Good morning, everyone. I hope you had a restful evening. It's a pleasure to welcome you back to the second day of İZPHOTECH event. Yesterday's discussions were insightful and engaging, and we are confident that today will be just enriching. We have an exciting lineup of speakers and topics ahead, so let's dive into another day of exploration, knowledge sharing, and collaboration. Thank you for being there, and let's make today as impactful as yesterday. Enjoy the sessions. It's my pleasure to introduce Professor Serdar Özçelik, distinguished figure in chemistry and device physics. With a PhD from City University of New York, he's been a key figure at İzmir Institute of Technology, pioneered departments, and making remarkable contributions. As a former dean chairman, Professor Özçelik directs cutting-edge research on quantum dots impacting display technologies. Today, he shares insights into his innovative work. Please join me in welcoming Professor Serdar Özçelik.
Okay, my voice. Okay. Thank you very much for the invitation. Thanks, Jana. And I'd like to welcome all of you. Nice meeting. I will give some brief information about the quantum dots. Well, even I am labeled as a device physicist. I cannot say anymore the device physicist. Mostly, I'm a chemist and quantum dot chemist, let's say. Yeah, in the past, I was engineer physicist. Still, I have roots in the engineering physics, but mostly I'm dealing with the chemistry the last almost 25, 30 years. And today I will talk about quantum dots as display materials. These are my students, almost most of it, and I thank them sincerely for their contribution. I consider them the scientists who perform the work at IYTE, all the nanoworks, and of course the funding from, well, its former name, the DPT. Well, for me it's still the DPT. Now they call the State Strategy and the Budget Office of the Presidency. Well, anyway, this is a DPT. So I established all of my laboratories, all the instrumentations with the supports, and then additional supports from the TÜBİTAK. And I'd like to mention these three scientists. We worked recently in the almost 5-6 years. Seçil is my PhD student. Now she's working at the Kansai Altan. Halide and the Hakan were students of the Canan Hoca, and Halide is working at the Ege University. Hakan is still here. Someday he will get his PhD. And many of the information I will share today is made available by the funding from the TÜBİTAK. That is the team members of the projects, and with all of us. Yeah. Okay, and all of us made a big contribution. And Doğa is our academic granddaughter. She was there, and that's just some in front of the glow box where they made the devices. And funding from the TÜBİTAK and the President's Office. So I will give some very brief information. I met the quantum dots in 1994. I was a PhD student at the University of New York. I was trying to make and tune the J aggregates. It's a supramolecular structure, and I was dealing with exciton. So I thought that, oh, quantum dots, that's another exciton material. So there was something. Well, I thought I may start working on it. I started working on the quantum dots as a young faculty member at Bilkent University, but not able to synthesize it. The reason was the Sigma Ultra refused to send the precursor materials. They told me that, well, I can make the semiconductor materials. Yes, that was the idea, and it's not allowed to send it to Turkey. Well, whatever. And I started the QD research at İzmir Institute of Technology. after some brief stay in the United States, and I learned some biology stuff there about in 2.5 years. It's kind of second PhD, actually third PhD for me to understand the biology part. So these days I'm also dealing with a lot of the molecular imaging and the application of the quantum that's in medicine. Of course, it's honor to share and to honor them. This year's chemistry prize is given for the discovery and the development of the quantum dots. These three scientists, Magni Bowendi, Louis Bruce, and Ekimov, made a contribution. Ekimov and Louis Bruce made the discovery of the quantum dots in a way. Ekimov made the quantum dots in glass material at low temperature, copper chloride, and showed it's linearly, its size and the absorption properties are linearly proportional. Louis Bruce made the quantum dots in reverse micelles, cadmium sulfide quantum dots in reverse micelles, with the idea of controlling the size of the particles. Bowendi made a contribution for the discovery of the synthesis method. But I think another scientist, maybe he has to should get the Nobel Prize, but probably some limitation in terms of the number of people sharing the. So he is I think he made enormous contribution to the field of quantum dots, and now he is the president of the University of Chicago, where he received his BS degree in chemistry. Now he is the president of the university. Well, what's quantum dot? Let's start with this one. Well, it's a semiconductor crystalline particles in nanometer scales. We have let's say, sort of computer modeling. So atom by atoms are aligned, and then real image and the high resolution electron microscope images. So that's really, we have the semiconductor crystals in the nanometer. Particle size typically from 2 to 15 nanometers, depends on what type of quantum dots you have. If it's, let's say, cadmium sulfide, after more or less 5 nanometers, then it becomes bulk material. So after 5 nanometers, it's a quantum dot. But if it's a, let's say, mercury telluride, it goes up to 15, 20 nanometers. So it depends on the size of the atoms. So it makes some impact on the particle diameter, and typically there are around several hundreds of atoms in a particle, and depend on the synthesis, you may have 10 to 12 and 10 to 16 particles per milliliter. So it depends on the synthesis, but you can make a lot of quantum dots in milliliters. And so in these days, it's possible to synthesize in a batch about kilogram level of quantum dots. Of course, not we are able to do so, but there are companies, especially in the United States. Nanosys is the main manufacturer of the quantum dots, and they are producing about 100 kilograms a day. And they mainly use the batch reactor with a size of 500 liters. So of course they are not saying it, but when they announced open positions, they put the whatever the skills and the work environment, and then you understand that they are having around 500 liters of batch reactor. So it's to make a reactor is quite engineering skills, and then that directly affects the synthesis, production, and the properties of the quantum. The properties of the quantum dots, they mainly the spectral properties of the color. Absorption of emission colors will be tuned by the particle diameter, particle size, or the atomic composition of the particle. And these particles are colloidally stable and thermally stable. And that means you have the solid particles suspended in liquids. That's the colloidal means. The colloidal stability also means there's a charge balance between the particle and the solvent or the solution. So you have to work with this a little bit. But these parts, of course, these are for the colloidal quantum dots. There are other type of quantum dots they call epitaxial quantum dots. It's made by the vapor deposition techniques, not with the chemistry techniques, but these are the two different type of material, and well, there are showing some similarities, but there are some differences as well. The name of the quantum dot actually introduced by scientist Mark Reed. Actually, he is a physicist, and he was trying to make the epitaxial quantum wells and epitaxial quantum wires. And he realized that quantum dots are the object confined to it says the zero dimension. Of course, they had a certain dimension. The particle is a certain dimension, but the size of the dimension is so tiny compared to the sort of bulk micron scale, millimeter scales of the materials. That means basically film, solid state films. So compared to that one, it's like a zero object. So therefore, he named quantum dots, and from there it's used as the quantum dots. Why it's important? Well, first of all, it's now in commercial use, in television. Probably most of us are aware of that. QLED TVs or quantum dot TVs. Samsung started to make it, and there are some other companies. And it's also used as the computer in the computer monitors, as Assoc uses makes the computer monitors, which has the quantum dots in the illumination part. So the quantum dots are the light producing component in those TVs or other display material. What does that mean? Actually, it's a material that produces the light by using the either light sources, but in generally, like in the LEDs, light emitting diodes, it is the material that produces the light itself using the electrical energy. So we are converting electrical energy into a form of the light as another form of energy. So that the material is just a transducer, taking one energy, one form to the another form. But for us, like this, all of these light sources are generated within a material. It's not something quite magical that comes from the material itself. These are the applications and some important points of the quantum dots. Of course, the chemistry, colloidal chemistry plays a role about the spectral properties as well as other optical properties. I'm especially mentioning the spectral properties because we most of the time refer to use the word optical properties, but that has some other meanings. So that's why I refer to use the spectral properties. That means the spectrums are tuned. That is the reason. As you see, there are many areas of the quantum dots may be used, and it's already using displays and cameras. It's on its way to use in medicine as the components, as a part of the diagnostic tool. It's also in the way of the sort of treatment, but still there's a main problem. The majority of the quantum dots produced in the lab, made in the laboratory or produced in the facilities are using cadmium based mainly. Well, some of them are the indium based. It's fine, but still all of them has some toxic properties. I did almost lots of studies on the toxicity level of the quantum dots. It can be sort of prevented by making this core shell product structure, but still it's difficult to convince the people the cadmium or lead based heavy metals makes some impact on the human being or in the environment. Yes, that's true, but there's an exaggeration as well. That's mainly the insights through some commercial businesses that needs to make money. That is the reason. But in some aspects, such as for the night vision cameras, it still uses mercury cadmium telluride. That is the main component. and they are not mentioning any about it, or they are not making any complaint about it, because they cannot technically repeat with another material, at least currently, or maybe for some in some seen future. So that's why it has to be somehow modified. We have to modify our mind, or adjust our mind. Another probably the impactful area would be quantum information. The quantum that's sort of now it's in its way to be used as the material in the quantum information, or to convey the information from one source to another source, and you can easily hide the information within the information by using the quantum dots, because it allows you to manipulate the information with something. That means you can play with its energy level. That's nothing else. That there is no magic. But people, when they say the quantum information, something catch words, but we are playing with the energy levels. For a chemist, it's doable, and then we can do a lot of magic. And the another importance is the market size. When the information are given as a market size estimation, like here it says that $15 billion to reach in 2028. There's a misleading information in those reports. The $15 billion is all of the products produced, like the television and the computer monitors. The contribution of the quantum that's within one television, it's about, depending on the size, but more or less about 20 milligrams. Nothing much. So 20 milligrams is not much worth it, and more or less the gram price, the unit price of the quantum, that is about $100 per gram. Not much expensive, but when we consider the amount to make is the necessary money to make the quantum dot, it's really less. It's around $1 per gram, more or less. Materials cost, not the involvement of the humans or the investments, but probably it will go up to $5 per gram. So you will make $95 out of it. So it's not nice profit. Anyhow, there are companies, mainly the Nanosys is the main manufacturer, but also DuPont is making. There are some other smaller companies making quantum dots, but the Nanosys is the manufacturer. Samsung is the manufacturer of the QLED TVs now. These days they are making it's called Neo QLED TV. It means the pixel-based quantum dots. It's sort of electroluminescent quantum dots is used. Sony Philips are also making. Asus makes the computer monitors. Osram Ridge makes the illumination lamps. In Turkey, A.CLaveria and Vestel uses the Samsung display, and they are making the QLED TVs, but mainly it's Samsung. And Hisense, the Chinese company, is using the BOE quantum dots. That's also a Chinese company. BOE means Beijing Optoelectronics. They are making the colloidal quantum dots, as well as some other material. Okay, the advantages of the quantum dots first. It's in the liquid form, like this. So it's processable. So it's like paint. You can do a lot of things. And there's no restriction. Another important thing for the quantum dot is the color purity. So that means their spectral bandwidth is so narrow. So for cadmium-based quantum dots, it's typically 20 nanometers. For perovskites, even less. But when we compare them with the organic light-emitting materials, the organic light-emitting materials, it's a little bit broader bands. That's its nature. You cannot change it. But for quantum dots, you can change the bandwidth, playing with the size and playing with the composition of the particle. For a chemist or colloidal chemist, it's doable. It's in your hands and you can do that. And probably you can squeeze a lot of them into a very tiny space. And when you put lots of atoms in tiny space, you would expect that some quantum phenomena will arise. And then we can still explore that phenomena. Tunability, because of the narrowness and wherever the emitting wavelength you want to do it, you can do it precisely ±1 nanometer. If you want to do it in 520, you can do it 520. If you want to do it 521, you can do it as well. So that gives you lots of play in this. It's called color gamut, and that's important for the TVs and the display systems. So you can go to the edge to the pure green, pure blue, pure red, and pure yellow. Actually, if you make the TVs with the four colors, it's much better. It's much real appearance on the screen. I have one. It's about more or less 20 years old, sharp, 4-color TV. It is still better than the QLED TV. It's still working. It's an LED TV, but it works very well. Scientifically, the quantum dots are 3-dimensional objects. In reality, that's even said it is 0-dimensional. It's a 3-dimensional, and it's a 3-dimensional covalent bonding that makes the quantum dots highly stable. It's a 3D structure and the covalent bond. And of course, there are some portion of it that's the ionic component. We know that the covalent bonding is not the pure covalent bonding, it's also partial the ionic bonding, so that gives an extra stability to these materials. These are really very, very highly stable materials, so their melting temperatures actually are about 1000 degrees Celsius. Of course, there are organic layers on top of it, the inorganic parts. So inorganic parts, they goes up to about 1000 degrees Celsius. But for the organic parts, it starts to decrease to around 200, 300 degrees Celsius. So when you make the device, you have to take those into consideration. For colloidal chemistry, for colloidal quantum dots, scale-up products or scale-out, that means manufacturing is possible. Nanosys achieved that. It's as I mentioned, high value-added product. Its price is $100. It's a gram, but for this, if you are buying some level of the kilograms, it's $100. But if you are buying some milligram levels, so you have to pay around $500 to $1,000 for scientific studies or for technical studies. That's the fact. Yeah, the manufacturing cost actually is about $1 material cost. Therefore, that it requires actually low investments. So in my laboratory, probably I can go with the scales, not in a day, but in a month, I can produce a kilogram easily, not a problem. Low power consumption means in two different ways. One is it's synthesis or production. You don't need high power, high electricity, lots of electricity in terms of what level. And also when the colloidal quantum dots are used, it consumes less power. That is the reason, it means the low power consumption. Well, at İYTE, I call İYTE İzmir Institute of Technology. I don't like its English name. It's as the İzmir Institute of Technology. I prefer İzmir Yüksek. That's what I call İYTE. My laboratory mainly focused on to make the ternary and the quaternary quantum. What does that mean? There are 3 or 4 different atoms within a quantum. That's because the binaries are lots of laboratories in the world, and lots of the companies are making the binary quantum dots, but some relatively less number of laboratories are making ternary and quaternary colloidal quantum dots, because there are it's relatively tedious, but it gives a richness in the colloidal chemistry, so you can explore many facts by using the 3 or 4 components in your quantum. That is the one of the reason. The other reason, when we started to do research in 2007, so we started making the binary ones, but we didn't like it, and then somehow, and then students had some difficulty to make the synthesis in the laboratory, and I said, mixed all of them, let's see what happens, and turned out it's much better. And then from now on, we stay to in ternary and quaternary quantum dots. So this is the electromagnetic spectrum range, we know. And this is the part in the visible range, and those are some of the materials, quantum dots, colloidal quantum dots we made in IYTE. Also, we made some of them in the near infrared part, and the mid infrared and the long wave infrared and terahertz region. Actually, I designed, but we haven't synthesized yet. Well, actually, I got a funding from TÜBİTAK, but I returned it. I said, I'm not going to do that because of the budget you are giving me. It's sort of insulting. I refuse to do that. I will not do that if they not provide enough money. Why allowed quantum dots? There are, see, there are 3 some papers showing that mainly the increased performance in the devices because of symbiotically it's taking the both advantage part of the 2 different binary quantum dots within the ternary quantum dots. That is the one of the reason. Scientifically, there's an enhanced quantum yield like those. That's the one of the first example. Cadmium zinc selenide material. It has the controlled enhanced quantum yield, controlling the alloy composition. The main contributions actually very tiny. They are, you can start with around 2 nanometers, 3 nanometers without shell protection layer. And you can go up to almost 100% quantum or whatever. So in laboratory, we achieved about 95% quantum yield with a 3 nanometers of quantum dots cadmium sulfide selenide without any core protection. It's so tiny. I think we made it around 2010, 2011. And after a year later or 2 years later, Bob and the group made the similar material and they published in Nature. They are MIT group. I cannot publish in Nature. Another importance of the alloyed quantum dots gives you the high spectral, wider spectral tunability. So you can cover the whole visible range of the electromagnetic spectrum with the one material without changing its size, just the composition tuning of the material. The importance when you have the same size of the particles giving the different colors, it's much easier to build the device. So one material around 3 nanometers, the other material is about 5-6 nanometers, and that will problem when you make the film. Therefore, we prefer to have the materials with the same size, that is quantum dots, the particles will be the same size. Synthesis methods, I will mention some of them by name and then some details. It's got one pot aqueous approach, one of the papers, and 2-phase approach. We use this 2-phase approach a lot. Of course, we also use one pot approach a lot in the laboratory. Then the hot injection method, that is the method when they discovered or they actually provided to the world. That is the way to make quantum dots more reliable and relatively with a high properties, high qualities. The hot injection methods works at relatively higher temperatures, but it provides very nice material. When the people started hot injection methods in 1992, 1993, they were using highly toxic materials, dimethyl cadmium, dimethyl zinc. So they are almost vaporized at room temperature. So it's highly toxic, and if you inhale about 5 milligrams, you are dead. That's serious. So you will be dead. That's why we never use those type of materials. We cannot use it because of the safety issues of the rest of the students. We don't want to use it, and we didn't use it because it requires a sophisticated equipment to control the vapor and its transport from let's say from the tube to the reaction to the reaction vessel, so the reactor. So that's really something really dangerous, and you don't want to do that.
Which is actually dangerous? Selenium?
Cadmium. Yeah, the cadmium is the most, but it's in the vapor form. So yes, as an ions, it's easily dissociates from the metals, and then you have the cadmium ions. That's what happens in the reaction. So you dissociates the material, and it's dissociates. It's in the vapor form. You can easily inhale. Then it's in your blood. You are dead because it changed the three-dimensional structure of the proteins. It binds to the zinc domain in the proteins. And that's why it's dangerous. The same thing for the lead, because these are 2+ materials. They are binding to the same domain with the zinc and the calcium. So the zinc and the calcium are two important the ions within our body. So all of the functional properties and the dimensional properties of the proteins are actually governed by these 2+ materials, 2+ ions. That is the reason. And when you look at the toxicity part, so you study lots of biology plus medicine. You have to do that. Otherwise, you prepare materials and you don't know what's going to happen. You don't want to do that. The other methods are solvothermal and the organometallic approach, and we are not using that. In solvothermal, basically, you are using a calorimetric pump, still make materials. For organometallic, you are using the organometallic materials to decompose first and then the associates. That is. So in the one-pot approach, so basically you have a glass balloon type reactor. It's something like this, nothing else. Okay, just you have some control input output gas and materials, and then you heat it up from the bottom, and you put inside. It's called magnet. So you stir them. That's what happens. With the heaters, you can go up to 300 degrees Celsius easily. But for the one-pot aqueous methods, you usually work around 100 degrees Celsius. Of course, there are some argon gas to prevent the oxygen in the air, as well as the vaporized water. That is the problem causing, not the oxygen. Vaporized water is the problem. So you want to get rid of the vaporized water. So you put your precursors, metal precursors could be here in this sense. It's zinc precursors, and there are capping agents. That means they are surfactants, nothing else, in terms of the chemistry language. That it's long carbon chain groups with some water soluble parts. That is the surfactant. That's actually we are using at home. Soap, detergent are all surfactants. And then you prepare other precursors like non-metals, sulfur, selenium sources, or tellurium. So these are the main sources. So we use here sodium hydrogen selenide and thiourea as the thiourea as a source for the sulfur. It's commercially available. We prefer to use the sodium hydrogen selenide. That's our main selenium source because we start from the powder and we make this material. These are not commercially available because they are sensitive to the air, so you have to make it yourself fresh and then keep it under the nitrogen or argon gas to prevent the interaction with the oxygen and the vaporized water. Otherwise, they will oxidize right away, and you can see they turn into black, so you don't use them. So you mix them, then well, chemistry starts working, yes, acting and talking by itself. So you make the material. That's our part is to select the materials, to select the precursors depending on their relative reactivities to each other. So the reaction will be in seconds, will be in minutes, will be in hours. So it depends what type of precursor, that is, what type of molecules you are selecting. Okay, that is the reason, because they have to decompose, and then after decomposition there will be reaction. So the rate of the decomposition is actually the bottleneck for the reaction. And by using time, you can grow the material. So by that way, you control the size of the particles. So the reaction time is your parameter to control. And by making control, you can select or tune the spectral properties of the materials, that is the colors. And as well as by making the good chemistry, you can control the bandwidth of the spectral bandwidth of the materials. The two-phase methods we use a lot, and used a lot in the laboratory. It's originally, I think it's discovered for the colloidal gold formation. So to make gold particles. Usually gold nanoparticles are made with the sort of aqueous-based method, Turkevich method, that well, in history they made the gold nanoparticles about in BCs 1,000, 2,000 years ago. But when they mixed the gold with some other materials, and they used as the stained glass in the church for the decorative purposes. When they look at it, they actually the colloidal gold. Similarly, Faraday make the colloidal gold in glass, and it's still in the British Museum. It's still stable. More than 170 years. Well, anyway, for the two-phase methods, we prefer the cadmium, zinc, or metal-based compound by using another material, myrostat, oleic acid, etc. So to make a compound. So some of them commercially available, but most of them are not commercially available. So you have to make it yourself. So you dissolve them in the toluene nonpolar compound, and you prepare your other source, non-metal sources, sulfur, selenium sources in water. So you are mixing tolu and water. So actually there are two different phases, non-polar and the polar liquids. Then they create an interface, atomic layer interface, and all of these particles are made in that tiny interface, about a few angstrom-thick interface, and that gives you an enormous ability to control the size of the particles as well as the spectral properties. It gives you about 95 to 100% quantum, that is almost perfect crystals. That is the meaning, and very tiny size with the 2, 3 nanometers, 4 nanometers. And it also gives you the ability to play with its atomic composition precisely. That is the reason we stick to this method, to make two-phase methods. It's for the quantum dots. I think it's discovered in China by Penn's group in 2004. They were using the Photonics material, the reactor, in steel reactor, and they were making the core shell type of quantum dots. So we made ternary quantum dots in glass reactor at low temperature, low pressure. So you mix them, and then at around 100 degrees Celsius or 90 degrees Celsius, you prepare the colloidal quantum dots. It's, if I'm not making a mistake, around milligram per milliliter concentration you can make it. But you can adjust it. It could be the higher level of amount or density could, as the concentration will be obtained. If you change the microscope, the smaller ethyl-hexyl octane groups, it's smaller groups, but it increases the solubility and dispersibility of the particles a lot. So I think we reached to something 100 milligrams or 150 milligrams per milliliters of concentration. It's really huge. And with that way, you can go over kilogram levels in a day easily. And so this is a two-phase, and what you see here is all of the particles are in the toluene phase, not in the water phase. What happened? All right. Some spectral properties. So you can, this is photoluminescence properties. You can tune and change the photoluminescence properties by just changing the atomic composition. And it's some XRT diffractogram shows the changing the composition. Of course, we made the analysis with the high resolution EDX-TM and some other methods to verify that yes, the composition really we are tuning the composition, not the size. We also do the measurement. We always do the monitoring with the size and the spectral properties during the reaction. That is the Bowendi's method. Similarly, a similar methodology that they were using, as I mentioned, relatively highly toxic compounds. But then they show that the tunability of the absorption properties absorption spectrum. And in those days, the quantum yield were really low, but within the years, quantum yield, that means the brightness of the quantum, that's increased a lot. In the hot injection method we use in our laboratories, we use the oxide, cadmium oxide or zinc oxides, because they are cheaper. It's easier to work with it because we are going up to 300 degrees Celsius. So you can dissociate this ionic compound. These are the ionic compounds. So time goes by, I have to go fast. And in the octadecene, that is the main solvent we are using. And then you can prepare your sulfur and the selenium sources, but now you are using a different type of coordinating ligand. 3-octylphosphine is the ligand mainly we are using. So that gives the better reaction with the metal sources. Depending on the addition, if you add very quick addition, you can make the material core part, but by adding drop by drop, you can add the shell part. So depend on what type of material structure you have. So it depends. That gives you the ability to make the tunability. So these are some information. So to make a colloidal quantums, you have to design the chemically design them. The chemical design means the synthesis methods you will prefer, reactivity of the precursors, the amount of the precursors, reaction volume, temperature, time, the material cost, and the yield, how much you produced or synthesized. These are the chemical design parameters. So that's our magical tool. That's our toolbox. That's in our mind, not written some anywhere. So we use our chemical knowledge and then we put them into work, and then the particle is made. When you design quantum dots, you have to keep in mind what application it's going to be used. If it's going to be used for, let's say, for display, you want to prefer to use some hot injection method because it's basically in non-polar solvent when it's produced in the liquid form. But if it's going to be used for medicine or biological application, you want to prefer to prepare in aqueous solution, that is in water, because if you change the organic layer around quantum dots later on after the synthesis, you mostly made some defects on the surface of the particle, and then that affects all spectral properties, including its brightness. So then utilization will be actually sort of degraded, not very good. These some, since it's a chemistry, yes, you put there some chemicals. You can transfer your knowledge. There's some part of the chemical knowledge we know as the know-how that we discussed anytime with John. Know why. We don't share the know why. This is our proprietary. This is who we are. So we cannot sell ourselves. We can share how we do it. Okay, this is the material. You can choose this one. That's the temperature. That's the reactor. But don't ask why I choose. Okay? So that's mine. We use batch reactors to test the chemical design. That means you are making a small volume of reaction, typically 50 to 100 milliliters. In some cases, people are making around 5 to 10 milliliters, but 50 to 100 milliliters is better because you have to test, you have to do lots of measurements. Therefore, 50 to 100 milliliters of reaction volume is good. And you can make lots of different quantum dots. An example, zinc cadmium telluride, about the tuning the spectral properties. So two different ways showing that if you control the reaction time, you can control the particle size because you let them to grow. When they grow, the bandwidth between the quantum dots energy level is getting smaller, and therefore it shifts to red. But you have to show that through the size measurements, the particle size is getting larger. But in the meantime, you have to measure the atomic composition of the particles by utilizing many different methods. You can use this electron microscopy elemental analysis, or you can do atomic emission spectroscopy or mass spectroscopy methods, and then you can really show that the atomic composition is not changing during the reaction time. So by that way, it's a proof that the spectral properties is just because of the particle diameter. Or the opposite, you have to prove that the particle size is same, but you are able to change the composition, and then those spectral properties are changing because of the composition. The trick here is not the trick, but you have to monitor the reaction tediously, spectroscopically, and in terms of the size. Because when you change the compositions, that means you are changing actually the amount of the precursors, initial mole ratio of the precursors. Okay? And depending on the different amount and the different mole ratio, different reactivities will be possible. Therefore, you have to bring your particle to the determined size, let's say 5 nanometers or 10 nanometers. So therefore, the reaction time will change. You cannot say about 5 minutes or 10 minutes reaction time. And by controlling the composition and the size of the particles, you can tune the band gap. That's the color. And it shows how we adjust atomic composition by changing the initial mole ratio versus the fraction or the mole ratio of the elements within the nanocrystal split. And there's also additionally, you have to do mass balance. So what does that mean? We synthesize the material, we purify them, and we don't discuss the rest of it. We do the chemical analysis, and then we do the mass balance. That means all together in beginning of the reaction and at the end of the reaction, pure materials and the discarded materials has to say. And that's what we do to check the composition. And by changing increasing the amount of the initial amount of the zinc in the zinc cadmium mixture, we tune the compositions at the beginning. So So 1 to 2 to 1, 3 to 1 ratio. Seems the cadmium is more reactive, even it's less amount toward the tellurium. 4 to 1 is approximately, that means both of them has similar reactivity toward the tellurium. But if you go 5 and above, then zinc becomes more reactive because more zinc ions is available around. That's the reason. Not the really attacking is not changing, but the availability of the zinc ions is more than it surplus the cadmium reactivity. That is cadmium running fast, but there are more zinc. Okay. I passed this part. This shows how we make the mass balance and the measurements. That's another example with the quaternary material of adjusting the size and the composition. And recently we discovered that in materials, the pyroxyl phosphine we use, we had two different commercial sources, and then we figured out there are impurities in it. That impurity is turned out to be 1 octanol, and the amount of the octanol also makes tuning of the size of the particles. And through the NMR spectroscopy, we understand that there are some octanol adsorbed on the surface of the particles, restricting the size of the particles. If the amount of the octanol increases, the growth of the particle is restricted. Therefore, the smaller particles are obtained, and we show that the size distribution, the compositions will be tuned, and it's selected as the cover art in the journal. For the manufacturing part, that means the mass production. So the keyword is the commercial, scalable, and economically sustainable mass production. That's the manufacturing, okay? Not something else. And there are, so the main economy in it. The science and technology is a little different. But when we say the nanotechnology, that means we should have an ability to control one atom at once or one molecule at once. So atom by atom or molecule by molecule, not all of them at the same time. So that's the sort of nanotechnology. Scale-up production is doable. So we use batch reactor. So this is sort of design and constructed in the laboratory. There are many control units. This is basically some sophisticated control, nothing else. But the reaction volume is from half liter to 2 liters in our laboratory, but it can be 10 liters, 20 liters. You can select, but then that means an experimental cost trial, it's getting really expensive because you are using lots of precursor materials, and some of them are expensive. So for half liter, like if you put the ultraviolet light, you see it turns to some yellowish and green color. And the similar properties are obtained. The production rate about 10 grams a day, but not in one batch, within probably a few batches. We also use a flow reactor. In the flow reactor, there are reactor parameters has to be controlled, or it's all controlled by the computer and the software and the pumps and other properties. Here, the reactor volume is so small. It's usually typically 2 milliliters to 20 milliliters. 20 milliliters means mass production. 2 milliliters test level. The advantage is you have capillary channels, small micro level capillary channels. So the mass is, the material is passing through those small channels, and there is a much better heat control and the temperature control. So it gives you some edge. It's you can make some reactions, especially for flow reactor. You have to choose a fast reaction, something reaction taking place in seconds, not in minutes or hours. There's no point. If the reactions are in minutes or hours, then it's better to use batch reactor. But seconds, the flow reactor gives you the advantage. Flow reactor means it continues. You start in the morning and come back in the in the evening, something like this. But in ideal cases, it's not the reality. So you have to be there actually. Someone has to watch the reactor is working, so it's actually smiling because it's also sort of tedious to work with it. So it requires postdoc level of skills. So with the laboratory, we use different source. We can control the pumps. We have different type of reactors, different paths, and then different path means residence time. Residence times is equal to the reaction time because the material flows within that microchannels. So they are passing through a certain tube. So the reaction takes place within that tube. So how much they stay there, it's the reaction time. Okay? And you can determine that residence times with the flow rate of the pumps. So we are using the pumps and the specialized valves, and then you can control. So of course, this sophisticated instrument has a sophisticated tech. It's $100,000. So I think there are 2 or 3 in Turkey. But mainly these flow reactors are developed for pharmaceutical business. Some of the it seems very nice instrument. It's really tedious to work with it. You have to make lots of optimization, and so you spend days and days and days to understand how to control this instrument. And many times we call England, Cambridge. Okay, we have this problem, that problem. Then they help us. And we learn during that time. But when you optimize the batch reactor or the flow reactor, they provide the similar spectral properties. Therefore, you can use either of them. And some I'd like to touch a little bit about the devices. I'm not expert. John, I should give a talk about the devices. But anyway, it starts with the color purity, again, compared to the organic materials. That is one of the reasons or main advantage of the quantum dots, and also the high stability. Organic materials also have high stability, but about how to prepare them, and then whatever the temperature required for the processing, that makes your material stability. Some differences. We made here at IYTE with the John's group fabrication of this quantum dots. That is the green OLED. That is the structure, device structure. I mean, we can talk about a lot, but mainly I think the whole transport layer is changed with the materials. Pure or doped material are used, and with that help, some of the electroluminescent properties and the current voltage properties are changed. Here, I think mainly we have seen some color-induced shifts by the voltage applied, and some charge accumulation between the emitting layer and the whole transport layer. Charge accumulation means increased capacitance and decreased device performance. That's what we learned. Okay. And then we utilize also inkjet printing technology. That's also highly sophisticated, and well, of course the price equipment about 75,000 euros. But you can make a device, but it's all big hype. It's also very tedious to use. Yeah, actually Hakan smiling from the holidays online, is listening to this talk. So that requires postdoctoral level of skills to use this instrument. The reason is that there are 8 different parameters, inkjet parameters you have to understand, and you have to play with it. So that means it involves physics, surface chemistry together, and the colloidal chemistry. So you have to have good understanding in all parts. So basically you have a nozzle, a small openings, metal, and you have the electrical field to control the drop and the space, drop spacing, and everything. I will just give some. So if you adjust the drop spacing, you can have a uniform line. That's what it does. Inkjet printer just makes a line. okay, nothing else. So by making the line, you can construct the film with the micron scale of precision. The instrument we use has about, I think, 10 to 20 micrometer of resolution. So you can have lines with a 20 micron width and the 20 micron separated from each other. That's the ideality. In reality, it's about 100 micrometer. Temperature also plays a role. Other factors are the ink parameters. Actually, you have to develop your ink. You have to formulate your ink depending on the instrument you are using. Not in each instrument generally use the same formula. You have to develop. So that means viscosity, surface tension, density are the main parameters, and it gives something this, but it says the printable ink. That means you adjust the viscosity, surface tension, density, nozzle, all the other the printing parameters, and then you can get the films. And these are showing the ink printed. These are film, not the device. But as you see, when you change the formulation, the film and the film quality is substantially changed. And we made inkjet printed red QLED. So we have seen that if you change again the whole transport material, you can adjust the turn on voltage, but usually this device has to be optimized because we had some short times and the COVID started at that time, then we stopped doing research. And we were able to demonstrate that we can make the passive matrix QLED display. That means it's a 16 by 16 device. So you have 256 pixels together. So we use classical way of spin coating, shadow mask, and then we had the inkjet printed display. The main reason Hakan had some magic to make the ITO patterning using the tape, and then the acid etching. That was the key actually. Otherwise, you are coating the area, this 3 millimeter, 30 millimeter by 30 millimeter area with the inkjet coating in the emissive layer. Otherwise, all other processes are more or less like QLED making. Yeah, we have the QLED sort of matrix. Hakan also developed the electronic part to control all the circuits. That is driving each the pixels, and I don't have the video, but it scrolls it scrolls on this display. So this is a demonstration. It's not really, oh, we made the display. This is nothing else, but we learned how to make display, and we developed step by step all the processing. That means the technology. So we know how to make it, and then we can optimize it, and we can do it much better. But that requires sophisticated infrastructure, that is the equipment. So with the very tiny budget, so we had $1 million. $1 million, million Turkish lira. So at that time, it was about more or less $200,000, more or less. So with this limited budget, we had some budget from the DPT, about 1.5 million Turkish lira, and then we used the two budgets together. For the conclusion, so we alloyed quantum dots designed, synthesized, and produced. Spectral properties can be tuned. Seems right now the flow reactors is a little bit favored in terms of the nanomanufacturing. Fabrication demonstrated with different techniques, with the passive matrix OLEDs, but still optimization is necessary to make. And that's my family, of course. That is with the enjoyment. And thank you. Sorry, it takes time.
Yeah, thank you for your beautiful talk. Very informative.
Thank you.
And many pictures to ask you in the future.
Yeah, sure.
Because I hope we can you know, your classical quantum dots.
Yes.
And we are trying to do the perovskite
And-
quantum dots. Position is more complex from the beginning.
Yes.
You have already taken cesium, lead, bromide, and then
Mhm.
you want bromide, iodide. But you want mixtures that go
Sure.
5 components. Have you tried or
No. I didn't study perovskite. One of the main reason is its stability. You know, the stability
I know,
issues. Yeah, now it's much better. And the other reason, and now it's in the other compounds, but it was using lead, and also the similar problem with cadmium and the lead and the mercury. But I didn't start it. That there are lots of people are making the perovskite, and its chemistry is not so complicated. It requires some skill.
I think chemistry is easier.
In terms, yes, it's easy. I don't want to use the word easy because it depends how you look at it. It might be easy, it might be tedious. Who makes the material? Yeah, it's just mixing, but mainly you have to, and I'm not you, the people have to have an understanding the level of chemistry, the involvement of those ions, because you are using ionic compounds, they will dissociate and then they will combine together. So you have, and people has to understand how those ionic compounds, how to handle them, mix them. The word is mixing is a very simple word, but in reality, as we mix
That's
them,
what I mean. Because
Yeah.
my students are chemists, they are able to make
yeah, they can make it.
If you're chemists like you,
Not-
you start doing that, and it will be real stuff.
yeah, lots of chemists are making perovskite, lots of them. So I'm sure they are very skillful, and then they can make the material. And probably in a few years, maybe within 5 years, we see the perovskite make devices. That's something like TVs. Maybe mainly the people are focusing, I guess, the lasers because of this narrowness of the material. I think it goes to about 5 nanometers full without maximum. So you can make some laser materials out of it.
The problem is that when you control the ligand instead of quantum dots, you get layers
Yes.
or wires.
Mhm.
That's the new dimension of chemical modification.
Um,
Control.
I don't know in the perovskite, are there something nanorods made with the perovskite?
Yes, not the wires.
Okay, then probably so that means you are controlling in one dimension, one dimensional growth.
Yeah, I can send you papers. You did lasers of the one dimensional perovskite wires.
Mm-hmm.
They do internal lasing.
Mm-hmm. But it's quite good because when I did PhD, the J aggregates we were aiming to make the laser materials. Actually, we did mirrorless lasing material out of the J aggregate. It's a molecular crystal, but you are tuning the size in one dimension or in two dimensions. It depends on what substrate you use. I was using gold nanoparticles, silver nanoparticles, and the vesicles, the biological three-dimensional structure, and the reverse micelles to control the size. And we were seeing some lasing effects. It's possible in the
Something similar. I want to change the topic.
Sure.
Second question.
Okay.
Your application diagram,
Mhm.
you show the salt concentrators.
Mhm.
When they make one, it goes inside the piece of glass.
Mhm.
Then there is a concentrator.
Yes.
But you did not show if any companies already
Because it's
doing
just
it.
it's there are some small companies, actually startup companies in the United States making solar concentrator.
Right. I think in Turkey also there is.
Yeah, I don't know. It could be. Canan may know because he has a roots in the solar cells. Is there any company making the solar concentrator in Turkey?
Yes, it is the glass, the top part of the glass, then from the side.
But organics. What they use? Okay, but I remember in Güneş Enerjisi Institute, they had the parabolic mirror sort of concentrating all the sun. Yeah, but they use some organic materials, right? Am I-
In Solar Energy Institute, they are still using concentrated sunlight
Mhm.
in order
To initiate reaction.
initiate.
No, but that is
Photonic
different.
reaction.
Yeah, it's different. I know that the solar concentrator, it's little different, but in Turkey we don't know. But it's possible.
Because that's one of the goals of my seminar.
Mhm.
Luminescent solar concentrator is you take glass
Mhm.
and you synthesize quantum dots inside glass.
Mhm.
When the solar sun comes, quantum dot create luminescence that cannot get out of the glass.
Mhm.
Goes
Internally.
internally and collects at the sides.
Okay.
Not only the quantum dots, some other organic materials, like minerals and diamides, act like that.
Mhm.
And yeah, that's a very good area.
Yeah, we may talk.
Area
We may
to
talk.
develop.
Okay, we may talk. Thank you.
Any other questions?
Okay.
I also.
Correcting. Thank you very much.
Thank you.
Yiğen has an announcement for us, as far as I know.
Thank you for this insightful presentation, Professor. So we have some connection problems for our next speaker. So we need a short break. Thank you.
Eğer bağlantı sağlanabilir.
Welcome again. Now it's my pleasure to introduce Dr. Anirban Dhar, Distinguished Principal Scientist at CSIR Central Glass Ceramic Research Institute, with a PhD from Jodhpur University and global recognition for his groundbreaking work in specialty optical fibers. Having authored over 110 SCI journal publications and holding 4 US patents, he has been honored with prestigious awards. Today, Dr. Dhar will delve into the world of specialty optical fiber, material selection, fabrication technology, and future challenges. Please join me in welcoming Dr. Anirban Dhar.
Thank you. Thank you for your nice introduction. And I'm extremely sorry for this miscommunication regarding the timing. So first of all, I would like to thank you, the organizer, for inviting me for this particular webinar. So I'm sharing my presentation. Just I think it is visible to everybody. Can you someone just confirm whether it is visible to everybody?
Yes, it's okay. Thank you.
Okay, thank you. Yeah. So today I am going to talk about the specialty optical fibers, materials, technology, and application. So before starting, I am from CSIR CGCRI Kolkata, which is a well-known research organization in India, and we are actually from the Council of Scientific and Industrial Research, which is located everywhere in India. And you can see that these are the networks of R&D laboratories, and we are from the Kolkata. Yeah, so this is our organization. Hello?
Yes.
Yeah. Okay. So this is our organization, CSR CGCRI, which is one of the first 4 laboratories set up under the CSR, and only one research organization which are working in India on glass and ceramic research. So now the R&D activities at CSR CGCRI are divided into 8 divisions, and our division is the fiber optics and photonics. Beside that, we have the energy materials, specialty glass, advanced ceramics and composite, membrane separation, bioceramics, functional materials and devices, and the refractory and traditional ceramics. Yeah. Now, in our fiber optics and photonics division, we are actually having the 3 verticals. The one part is the specialty optical fiber fabrication, where we are starting with the glass tube and then converted it into the finally preform and the different types of fibers, which I will talk just right after this slide. Now, after that, we have another vertical where we are using this optical fiber to develop amplifier and the lasers, and another segment where we are working on the fiber-based sensor technology. Now, so this is the content of my talk. So I will briefly talk about the optical fiber, followed by the types of fibers, then the materials used for optical fiber fabrication, technology for optical fiber fabrication, challenges ahead with the applications. So all of we are know about this particular picture. This is actually the COVID vaccine. We are all basically scared about this. Now, the 3 things which actually help us to come out of this are the COVID vaccination, the telemedicines, and the online classes. So we are all aware of these 3. And all these 3 are possible because of this glass and the optical fibers. So what is optical fiber? So optical fiber is nothing but a flexible, transparent fiber made up of generally pure silica glass, which has having a dielectric waveguide structure and generally cylindrical in shape. If we see this particular picture, it shows the micrograph of an optical fiber in comparison with the human hair, which shows that this optical fiber is slightly thicker than that of the human hair. Whereas human hair is 80 micron, the optical fiber is about of 125 micron, and when it is coated, it comes to be 250 micron. So what is the basic structure? The basic structure, all of you know that it consists of a core followed by the cladding and the coating. This core actually carries the light signal. Cladding keeps the light inside the core, whereas the coating provides the mechanical strength. And this is the refractive index profile, where the core have been the higher refractive index compared to the cladding. As a result, light propagates through the optical fiber by following the principle of total internal reflection. So this is all known to us. Now, a very common question comes to our mind: why this optical fiber? Why not the copper cable? Because there are plenty of reasons. As we know that the optical fiber has higher bandwidth, so number of information carrying capacity is much higher in case of optical fiber. It can carry the information much larger distance with a higher speed. It is immune in the electromagnetic as well as radio frequency wavelength. As a result, we have the security, and it is lightweight and thinner compared to the copper cable. Obviously, cost is little bit higher. So compared to copper cable, optical fiber is much more practical to be used. Another question comes: which one is better, optical fiber communication or wireless communication? Again, there are some reason where optical fiber having some advantage in terms of data rate and the distance covered. But wireless is also good. It has number of connections that cannot be given by the optical fiber. Again, the wireless is basically mobile in nature, whereas optical fiber is static. But the installation cost in case of optical fiber is little bit higher. So if we now compare this optical fiber and the wireless, then we can have that 5G is good because of its mobility, but without the fiber, the revolutionary goals of 5G would simply be impossible. So let us just see about the evolution of optical fiber. After that, I will go to the types of optical fiber. So it starts around 1015 by A.CLaveria, who has actually published the first books on the optics. And as a result of that, 2015 was announced as the International Year of Light. Then the 1842, Colladin actually shows that light can travel using the total internal reflection in a very simple experiment. Then Heinrich Lamb, who was actually the third-year medical student in 1930, prepared the first fiber optic endoscope. Then Narendra Singh Kapani, Indian scientist who is also known as the father of fiber optics, showed that light travel in bent glass fiber. Then the Maiman in 1961 invented the first laser. However, the major breakthrough comes in 1966 when actually Charles Cow in a theoretical paper proposed that it is possible to fabricate low-loss silica glass. Then the David Payne in 1986 demonstrated the first erbium fiber amplifier, and the circle complete when Professor Russell in 1996 demonstrated the first photonic crystal fiber. Obviously, from 1966 to 1986, there is a story, but that I will come during my later slides. Okay. Now, what are the types of optical fiber based on waveguide design? It can be simply divided into two categories. One is called the step index single mode, where only one information can go well, and there is actually the code dimension is very small, that is the 9 micron with respect to 125 micron cladding. But in case of multimode, you can have numbers of fibers, number of modes or information can go through this, but these have two different structure. One is called the step index multimode and another is called the graded index multimode. Now, which one is better? If we see the input pulse and the output pulse, it clearly shows that in case of step index, it is preserved. That is, there is no dispersion, but the dispersion is much more in case of the graded index structure. So much less in graded index structure. So graded index structure, graded index multimode fiber is preferred over the step index multimode. And if we compare the step index fiber and the graded index fiber, you can have a very clear idea. In case of step index single mode fiber, we have the higher bandwidth, lower attenuation, so it will be usable for CATV as well as telecom network. But for multimode fiber, since it has the lower bandwidth and higher attenuation, it is suitable for shorter distance, that is local area network connection. Now, based on types of optical fiber in terms of material, it can be simply divided into two categories, the silica as well as the non-silica. Now, in case of non-silica, it can be divided into oxide glass, non-oxide glass, and others materials. In terms of oxide glass, you can have telluride, charminate, phosphate, whereas in non-oxide glass, we can have the chalcogenide glass, halide glass. In terms of others, the polymers, crystal, and semiconductor. On semiconductor optical fiber, Professor John Belletto group is working significantly. Coming out to be the another types of optical fiber, which is not still stated, that is called the specialty optical fiber. What is this? This is actually differ from that of the standard single mode or multi-mode fiber to manipulate some characteristics of an optical fiber by selecting some particular waveguide design and doped with some special dopants. These particular fibers require a very small length for its application. So we can say its requirement is very small in terms of length, but its impact is very high. As you can see, the specialty optical fiber market is projected to reach around 2,130 million by 2030 with an average compound annual growth rate of 7.3%. So, what are the specialty optical fiber? This is one of my favorite slide. This is called the specialty optical fiber tree. You can have different types of specialty optical fiber, starting from polarization maintaining fiber, photonic crystal fiber, high index fiber, semiconductor fiber, rare earth fiber, radiation hard fiber, non-zero dispersion fiber, photosensitive fiber, band insensitive fiber, so on and so forth. Don't consider these are the only fiber. Could be various other possibility. I could accommodate few of them, but all these fiber are differ from each other in terms of their composition and the structure as well as their final applications. Coming into the steps in the development of an optical fiber. So we are very close to the actual preform fabrication stages now. So it starts with the preform fabrication, then it goes to the preform characterization before you go for the preform shaping. Of course, this preform shaping I will briefly tell, then the fiber drawing and the fiber characterization. So what are the important fiber parameters? This is a particular snap of the fiber data sheet. If you find in a particular commercial fiber producer or fiber supplier, so you can have lots of data, lots of information present here, but which are important during the preform fabrication stage? Let us consider the four important stages, that the loss or attenuation. This is actually depends on the glass composition and the fabrication process. So you need to be very careful about the selection of the material. And this loss or attenuation actually indicate how long the fiber can transmit your information. The second one is the numerical aperture, which actually depends on your selected dopantes and their concentration. And this numerical aperture is important to calculate what amount of light it will take up. Now the third one is the core clad dimension. It will depends on the number of deposition passes you selected, and this will actually help you to ascertain whether your fiber will be the single mode or the multi-mode. The fourth one is the dispersion, which actually depends on the waveguide design, and this will decide at which wavelength your fiber will be the best possible possibly used. So now we have understood what are the criteria, but now we need to see what material actually we need to select for fiberization. So as per the requirement, there should be different aspects. First requirement is the thermal. In thermal point of view, temperature stability is important, as well as it should be suitable for processing at high temperature. In terms of chemical point of view, it should be durable and non-toxic in nature. In terms of optical properties, it should provide the low transmission loss and control of refractive index should be there. In terms of mechanical property, it should have the control on the shape or size and should provide the necessary mechanical strength. In terms of the source, it should be easily available with high purity. So what material we can select? Actually, all of the elements present in the in the periodic table. So here you can see there are different colors. So one is the network modifier, one is the network former, one is the imperfect network former, like this. But the most important is the network former and network modifier. The network former are silicon, phosphorus, germanium, and the boron. So let us see what material we should use. So here is a comparison of different materials for optical fiber preparation. So you can see the different materials, their typical composition, their operating zone, and the transmission loss. You can see that different glass composition are uses for the different operating zones. But most importantly, the silica glass is found to have the lowest loss at around 1.55 micron. So other glasses could be also used, but that should be in the other wavelength range. So the silica is the best material for your fiber making. But it was not so an easy story for silica to be selected for this. It was well known of the silica glass from the Egyptian age. But slowly the glass is having the reduction of the losses. But still, that loss was not so good enough so that the optical fiber research is in a boom. But since in 1966, Professor Charles Cow published his paper on the theoretical background that it could be possible to having a low loss silica glass. After that, there is a significant reduction of the loss, and finally the fiber has been also been fabricated by the group of 3 scientists. So that's why Professor Kau has actually got the Nobel Prize in 2009 for this particular invention. So what is basically loss? Loss is nothing but the output power to the input power, taking a log divided by the length of the difference between the output and the input power. And it is expressed in the dB per kilometer. And you can see the 0.5 dB loss is actually 90% transmission. But if you go to the 3 dB, it's 50%, whereas 10 dB only 10% transmission. So most of the information is become lossy. So where is the losses coming in the optical fibers? So there are various types of losses comes. One is from the absorption, which could be divided into impurities, which can come from UV electronic or IR molecular loss. Intrinsic loss, which can come from wedge vibration or transition metal loss. From the radiation point of view, it could provide the microbending or macrobending losses. Then from Rayleigh scattering, it can arises due to the variation in concentration or variation in density. It can also provide losses due to the imperfection, which can create either by formation of bubbles, cracks, or inclusion. And finally, there are waveguide imperfection losses, which comes around the core clad interface. So there are the different transition metal ions possible, which can be incorporated during the fabrication unwantedly, and this could provide a very high loss, which is not appreciable for the fabrication of optical fiber. So here is a very brief history how this low loss optical fiber has been fabricated. So before the Charles Cow has predicted the low loss silica glass is possible to fabricate, Frank Hyde has already fabricated the pure SiO2 by the hydrolysis of SiCl4. And by that time in 1957, Lawrence Curtis has also demonstrated a particular fabrication technique, that is the rod in tube process for fabrication of optical fiber. And then after the prediction of Charles Cow, Derek Craig, Robert Muller, and the Peter Schulze actually fabricated the fiber, and they have published it in 1970. And this is an actual machine or instrument where they have actually fabricated this low loss fiber, that is the less than 20 dB per kilometer. As soon as this fiber was fabricated, Peter Schulze again successfully fabricated germanium dot multimode fiber using the OBD process, and then the drawing process is also actually optimized by 1977. So with this brief introduction, we have now understood that how this silica has come to be a particular material for the optical fiber fabrication. But still there is one point need to know before we go for the actual fabrication, where we should use this silica optical fiber, because there is a 3 window. The first window was at 800 to 900 nanometer, which was used initially at 1970 to 1988, and there was the loss around greater than 2 dB per kilometer. After that, it has been identified that the loss of silica is lower in case of at around 1310 nanometer or the second window, where it is used for 1980 to mid 1980, and the loss was around 0.4 dB per kilometer. But right now we are using it at third window, that is the 1510 to 1600 nanometer, and it is used since mid 1980, and the loss is around 0.14 dB per kilometer. So with this, let us identify the different process through which optical fiber can be fabricated. That could be divided into 2 stages. One is inside vapor phase deposition. Here what happens, you can vaporize the material and deposit inside a silica tube. That is why it is called inside vapor phase deposition. And in case of outside, you produce the vapors and deposit in the atmosphere, having a silica rod over the surface. So one is inside the silica tube and another in the outside of the silica tube. Okay. Now in case of inside vapor phase deposition, we can have the 5 process. One is called the modified chemical vapor deposition, which we will learn today. That is identified by AT&T Bell Laboratory in 1974. Then we have different plasma vapor deposition process, plasma CVD, identified or by Philip Research Laboratory in 1976. Then plasma enhanced CVD, again AT&T Bell Laboratory, plasma impulse CVD by Scott Glass, and the surface plasma CVD by CNET Laboratory, France. But this inside vapor deposition is usable for the short length of preform or basically the R&D purpose. But for the large amount of or the large size preform, you need this outside vapor phase deposition. That is having the two different stages. One is called the outside vapor deposition, which is invented by the Corning Laboratory in 1934, and the vapor axial deposition, which is identified by the NTT in 1977. But today we'll learn this modified chemical vapor deposition. So here is the schematic of an MCVD technique. You can see there are different liquid bath where we have the liquid precursor like SiCl4, GeCl4, POCl3, BBr3. So this precursor, when this oxygen gas bubble through this precursor, they will actually carry these vapors, and these vapors are going to the silica tube, which is rotating in a glass working lathe. And this silica tube is heated from outside by an oxyhydrogen burner, and the outside temperature of the tube is monitored by the optical pyrometer. Now, after this process is established, now first you need to deposit the cladding layer followed by the cold layer, and then collapsing to get the final preform. I will show you some videos so that it will be clear to you. So what are the basic steps? The first steps is the tube selection, tube cleaning, tube setting, cladding cold layer deposition, collapsing, and then fiber drawing. We will learn all these steps. So first is the tube selection. This is a snapshot of a silica tube provided by the heroes. You can find there are different types of parameters written in the left hand side. So which one is important to select a particular tubes? I know that it is very difficult to explain everything today, but still there are different properties which is listed here, like the dimension, which gives you ODID, ovality. Ovality means the difference of maximum OD and the minimum OD at a particular position. Then the siding, bone S is a very important, because if there is a bone S, your preform will never be the straight, and then there will be a variation in the fiber drawing. The CSA variation, and obviously the wedge content, because that will indicate or that will actually control the final loss of the fiber. So based on this, you need to select a particular tube of the specific dimension and the specific parameter based on the available tubes. After that, what we need to do? We need to clean it before we start it. So the cleaning is important, and one need to follow this series. First, you need to use the aqua regia to remove any metallic impurities, then the HF, then the deionized water, followed by the isopropanol and the acetone to make the surface water free, and finally the air dry to achieve the dry glass surface. So after the tube cleaning is done, you need to set it into the glass working lathe. So how it is setting? You can see in this right hand picture, there is some process is going on. This is called the alignment. This is very important. Why it is important? Because unless and otherwise this alignment is done properly, you will never get the straight preform. So after selection of the tube, cleaning of the tube, this alignment process is also important. But we need to be very careful about that. We should use the low temperature and achieve the tube straightness, so that there should not be any sagging occur during the preform processing. So here is the actual picture, which is actually given here to show you some idea about the tube setting process. Then the next is the cladding and the cold layer deposition. So this is important to achieve your desired core and the cladding thickness. So what are the parameters required? One is the vapor phase composition, that will depends your the refractive index refractive index profile. Then the deposition temperature need to be optimized properly, so that there should not be any bubbles formation. The burner speed also need to be controlled to achieve the desired thickness. And the laminar flow is important. What is laminar flow? So that during this deposition process, there should not be any disturbance during the deposition. If it is the laminar flow, you can be very sure that it will gives you the proper deposition. And the suitable internal pressure is also important. Now, just going into little bit, what is the process, the behind the process where this deposition is taking place? This is called the thermophoresis. This is called the thermophoresis process. In this thermophoresis process, what is actually happening? At the hot zone, the particle is produced due to the oxidation, and then they are deposited at the cooler region. But that is up to a particular region, that is called the deposition zone. After that, no particle is deposited, it just go away. So what are the different important parameters? This deposition length is proportional to the total flow rate within the tube and the thermal diffusivity of the gas, for which you need to introduce helium as one of the components, although it is inert in nature. Then the deposition efficiency is depend on the two temperature. One is called the equilibrium temperature, which is between the inner wall and the heated gas. And the second one is the reaction temperature. And your burner speed should be selected based on the burner hot zone and the reaction time. These are the different common dopants used in case of silica fiber fabrication. You can see except this fluorine and boron all have higher refractive index compared to the silica. So if you want to increase the refractive index, that is in the cold layer deposition, you will use along with the silica, phosphorus, germanium, aluminum, etc. And in case of the cladding layer, you can use silica along with the fluorine or boron. So here is the basic reaction. In the cladding layer, generally we use silica along with the fluorine or boron. Although I should say here, this boron is not a material right now used. It is only used for making of the PM fiber, that is the polarization maintaining fiber. So you can see the reaction are nothing but the simple oxidation, which are producing the corresponding halide gases. Now in the cold layer, again, we need to introduce silica along with the germanium and the phosphorus, so that the mixture of SiO2 along with the GO2 or SiO2 Pu2O5 is deposited with the higher refractive index. Now the last stages for the preform fabrication is the collapsing. This is important to achieve the desired core clad concentricity and the avoid central dip and the processing time. It requires the optimization of the hydrogen oxygen burner flow and the ratio, burner speed, which will decide what the time requirement. Then the tube rotation, positive internal pressure is important to achieve the core clad circularity, and the number of collapse passes will control if there is any central dip formed during the preform RIP or not. So the collapse rate is basically depends on the different factors like the pressure difference between the outside and inside of the tube, the surface tension of the glass, which is actually also depends on the how many layers has been deposited. So that means it is in terms depends on the inside and the outside radii of the tube, and the viscosity, which is a function of temperature. Here you can see in the right hand side a picture which shows that collapsing has been taken place. Now, finally is the fiber drawing. So the fiber drawing is important to achieve your desired fiber diameter, proper coating, and the fiber strength. It depends on the draw temperature, drawing speed, draw tension, the coating material used, and the UV power for curing. Here you can see the schematic of a fiber drawing tower where the preform is fed into the furnace, and then at a particular high temperature it gets melted and comes through the laser micromonitor to the coating cup, and then it is getting polymer jacketed followed by the UV curing to get the final fiber. And you can consider this fiber drawing is nothing but drawing of a cylinder of a thin dimension from a bigger dimension. Now I will just play a video which is actually showing how this optical preform fabrication is going on. So this you can see is actually preform fabrication setup or called the MCVD setup. You can see the burner and here is the control interface. So the tube is heating by the oxyhydrogen burner. Inside there are the gases. This is the collector tube and this is the input tube. Now you can see some reaction is going on. Here you can see this reaction is occurring during the deposition stage. And when the burner is passed over it, it gets converted into the clear glass. So burner is moving from one end to the other end and then moves very fast to the again to the left hand side or right hand side depending upon your view. So this completes one deposition pass. Now it starts the collapsing. You can see the two white lines. These two white lines are actually the core, but it needs to be collapsed to a single line. That is called the collapsing or the sealing pass. Now you can see this core layer is get sealed, and you got the core layer, and outside that is the cladding layer. Now we'll go for the fiber drawing. Here, as I said, this is the furnace where the preform is fed, and at a particular temperature it's softened and gets thinner and go through the diameter gauge where we actually measure the dimension of the fiber. I hope it's clear that you have got an idea about how this preform is fabricated and the fiber drawing is occurring. But here it is not the end, because we have not talked about any specialty optical fiber. So the specialty optical fiber must have some dopant like rare earth should be there. So it could be used as an amplifier for long range optical fiber communication or the CATV application. And you can see that this optical fiber amplifier market is also very huge. Yeah, so we can use the different dopant ions like this erbium, thulium, ytterbium, but as the silica is the best material for low loss fiber, and it is having the low loss region at 1550 to 60 material. It has the longer upper level lifetime and no excited state absorption, and it produces 100% quantum efficiency. But there is a problem that the rare earth solubility above 100 ppm is a question in case of silica fiber. So you need to introduce alumina or phosphorus. So the MCVD solution doping is required, not the pure MCVD process. Or you can use also MCVD VPCD. I will talk later on. And that is the reason why the cost of PDF is about $10 to $20 per meter, which is considerably high than that of standard single mode or multi-mode fiber. And not this material cost. This is because of the process cost or the technology cost, which indicates the higher price of rare earth. So you can incorporate rare earth through three different processes. One is the vapor delivery process, solution doping process, or the sol gel process. Now the solution doping process is the simplest because of its simplicity in terms of introducing different rare earths at a time. So here you can start with the deposition of the porous core layer. It will looks like that. So there are lots of porous structure is there. So as a result, after you deposit porous structure, you cut it and dip into a solution containing aluminum and the rare earth salt solution. Then the salt solution is drained off. You dry it and then sintered to get the soak layer, and then finally collapse to get the preform. During the soaking, you can see these layers, these particular layers which are pores, they are get completely filled by the rare earth and the aluminum. So what we need to know, what are the parameters that will control your rare earth incorporation? There are basically divided into two parts. One is during the shoot deposition, which depends on the deposition temperature and your vapor phase composition. And in the second phase, during the solution composition, we need to select a proper solvent, aluminum rare earth concentration ratio, dipping time, and precursor salt. I am telling you, this is so simple process, but when you go into the details, it will be very complicated. So I am not going into the very details. I will just show you some idea why these are the important parameters. If you see this particular picture, it shows that when you have the same composition, but you increases the deposition temperature from 1255 to 1295, your pores is become larger. As a result, what will happen at high temperature, if you deposit your porous structure, what will happen? The non-uniformity increases. You see the next curve, next picture. Here it shows this A is nothing but the deposition temperature porous structure or the pore size distribution at 1295, and B is actually the porous structure variation at 1255. So what you can expect that at lower temperature, your deposition is better, having more uniformity. But the rare earth incorporation will also be high, but only problem is that it will have lower addition to the silica glass surface. So during solution doping process, it have a chance that it can get out of the silica soot surface. So as a result, you need to optimize that process as per your requirement. So here are some papers is referred. You can go through this to get in more details. Now if we go into the compositional effect, you can see the compositional effect, how this shoot structure is changes from silica to silica germanium to silica phosphorus. So the basic idea is that depending upon your amount of rare earth incorporation, you can select your vapor phase composition. Silica is better for having good uniformity, but is worst in case of your basically strength towards the shoot strength towards the glass surface, and it has the higher chances of the rare earth clustering, whereas the phosphorus can provide larger incorporation of rare earth, but the non-uniformity is much more higher. So as a result, for RBM doped fiber, people mainly use the germanium doping. Now coming into the influence of selected solvent, what type of solvent we will use for making the solution? The solvent should not dissolve out the shoot. The dopant should have high solubility, and it should not produce any residue after the dehydration. So in terms of that, the best two solvent is the water and the ethanol. But we find that the rare earth incorporation is higher for alcoholic solution, and also the OH loss is much more in case of water solution compared to the alcoholic solution. You can go into much more details from this particular paper. Effect of solution composition. You can see even the precursor of the aluminium has some effect. If we have the same concentration of aluminum chloride and aluminum nitrate in solution, when you incorporate it into the fiber of the same shoot structure, you can find this aluminum chloride is introduced at higher level. So this is also true in case of the deposition temperature. For the fixed deposition temperature, if you increase the aluminum concentration, the concentration of the aluminum also increases. But here, the second hand side curve is a very important one. Here you have the fixed RBM concentration. Your RBM concentration is fixed, but you are increasing the aluminum concentration. So you can find that just only increasing the aluminum concentration, you can able to increase the RBM concentration. This is actually known as the cooperative phenomenon. You can go through this also through this particular paper. Now, why this aluminum? Why aluminum is necessary to increase the rare earth solution, rare earth concentration? Because it actually provides a solvation cell around the rare earth and reduces the rare earth deep formation in the fiber core, and it also improves the gain flatness through the star splitting. You can see this particular picture where this green ball is the RBM, which is surrounded by this red ball, which are oxygen, and the aluminium, which are this blue one, and the rest of these blue ball is the silica. So this is the complex structure which is actually formed during the deposition or during the incorporation of RBM in the class structure. But how much aluminum you can incorporate? Okay, there is a limit. After you increase the concentration beyond 3 mole%, there is a problem occurs around the core clad interface because of this phase separation. So this will increase the scattering loss significantly, and you need to use some procedure which is actually proposed, that use of fumed silica dispersed solution to overcome this problem. Now, as I told, this effect of dipping time is also important. So you can find that with increase in the dipping time, the rare earth incorporation increases, but it reaches a maximum after a certain time span. After that, if you also leave it for 1 hour or 1 day or 1 week, there is no further increase in the rare earth concentration incorporation. Even your selected rare earth precursor also have some effect. So all these you can having more details, why it is occurring, why this is occurring, all these things has been explained in this paper. So if you are more interested, I can share all this paper, you can go through this later on. Coming into the another important thing, RBM dot phase separated preform. What is phase separation and why we should interested to go through this? Actually, this is required to modify the local environment of RBM to increase the lifetime of 4i13/2 to 4i15/2 transition. This is actually occurs due to proper selection of the glass composition followed by the annealing, and when you have this type of phase separated materials inside your core of the fiber, and this aluminum rich phase separated within the core of the preform will help to increase the lifetime, and as a result you will have finally the spectral broadening of your fiber. Now the rare earth of high power laser. So laser is all known to us, which is light amplification by stimulated emission of radiation, and it has various applications in industry, medical, and strategic area. And the three most important properties of laser are that they are monolithic, coherent, and directional. And why these lasers are basically replacing the solid state laser? Because it has the high stability. This fiber laser has a high stability, excellent beam quality because of its small size, higher efficiency, good thermal management, small footprint, and the easy to operate. So these are the advantage of the fiber laser. And in case of fiber laser, ytterbium is the best dopant, rare earth dopant. Why? Because of its simplest energy level. It has the small difference between your absorption as well as the emission wavelength, and it has low quantum defects and provides high lifetime of the excited level. So if you see, this high power fiber laser market is also booming, It's targeted around 8.42 billion by 2030 with a CAGR of 14.51%. But there is a basic difference between the waveguide structure between the amplifier fiber and the laser fiber. While in case of amplifier fiber, you have a small core but high NA, but in case of laser fiber, you have larger core with small NA. And as well as your rare earth incorporation is also need to be very high in case of laser fiber. Okay, so what to do? We need to first see the basic laser structure. So these are the pump diodes through where the laser pump is coming through this WDM combiner to this fabricated cavity where the active fiber is placed in between two mirror. This mirror are fiber based mirror called the high reflecting fiber backdating and the low reflecting fiber backdating. And finally laser light is coming out. But why we require this double clad concept? This is very clear here. You see these are this red circle are the important fiber based component where this CSI CDCRI we are actually working. Now this is the double clad concept. So this your pump light or the pump laser diode is multimode in nature. So if you have a very small core, most of the light go unreacted without interacting with the rare earth. So your final output will not be very efficient. So what you need to do, you need to interact rare earth ion as much as possible. So that what you need to have, you need to use your cladding also as a part of your core. So that is called the double clad concept. So what we find after this double clad concept is arises, even this circular cladding is not a very good concept because most of the ray introduced into the cladding is basically goes away without interaction through the core material. So what is the solution? The solution is just to break the symmetry of the cladding layer. And here comes the point what I have talked previously, that the preform shaping is required. So how to break this symmetry? Now theoretically, it has been shown by the Professor Tunerman group that if you break the symmetry, the interaction with the core material increases and the efficiency of the fiber laser increases. So they have proposed various types of design. So initially it has been found this D-shaped structure is best. But unfortunately with this D-shaped core, it is very difficult to splice with a circular core. As a result, people has evaluated this structure. First this D shape is converted to the double D shape, then it goes to the hexagonal, then it's to the octagonal, and finally people are now trying the 12, that is the dodecagonal. Now these are the different fiber structure which we actually fabricated in our divisions. Now this large mode fiber area is established. We need to fabricate it. But how? It is not this MCBD solution doping technique because it sets lots of limitation. Vapor phase composition need to be optimized. Deposition temperature is need to be optimized. You need to have pre-sintering temperature. You need to increase the core layer to achieve the large size core. Solution composition may vary and the sintering condition also vary. So what we will do? Now we need to have different challenges to overcome this core thickness, non-uniform dopant distribution, poor process repeatability. So what is the solution? We need a separate fabrication technique. So what is that? That is the vapor phase doping technique. So what is the advantage of vapor phase doping technique? Here you don't need this to deposit porous structure. So you can deposit the rare earth simultaneously. That is the in situ process. So you can fabricate the large core LMA fiber. You can increase the dopant concentration significantly. You have a good control over the process, and the process is a reproducible one. But is there any challenges? Yes, there is a challenges. Condensation of precursor materials like the chelate materials, decomposition of the chelate, that is another problem. Rare earth concentration can vary along the length because of the non-uniformity of the vapor phase along the length. Lack of available reliable system. There is no such system available, and the whatever the system is available commercially, those are very complex one. So you need to optimize all those things. So this is a basic structure, schematic structure of the vapor phase chilled delivery system. So what is additional here? You had this SiCl4 in your MCVD setup, but these two, aluminum chloride and the rare earth chelate, are additional high temperature cabinets which are heated at high temperature, and helium is used as a carrier gas, not the oxygen. So this helium is basically used to carry this aluminum and the rare earth, and they are simultaneously deposited. So you have number of parameters to be optimized to get a particular preform of repeatable nature, and this is the actual structure of the system what you have already seen. But there is some limitation in power scaling till now, although we have achieved more than 1 kilowatt or 100 kilowatts of power, but still further power scaling is required. That is actually restricted because of some limitation like nonlinear effect, SBS, SRS. We have the transverse modal instability at high power for long-term application, thermal damage, and the photodarkening. So what could be the possible solution in terms of fabrication? One is the waveguide design. You can change some waveguide design. You can change the host glass composition. You can change the pumping technique. But since we are talking about the fabrication today only, so we are talking about the waveguide design and host glass composition. So photodarkening, what is photodarkening? It is actually the increased fiber loss because of the induced pump radiation. It has various reasons and various possible solutions. What is the reason? Most important reason, which is still not established, but people are thinking it is a possible mechanism, is the formation of color center or formation of atomic point defects. What is the consequences? That it will reduces the laser output power with time and reduction in slope efficiency, so the long-term stability of the laser is not possible. So the solution is that you can use the modification of host composition using the aluminum phosphorus, incorporate cerium as a modifier, modification of fabrication process, collapsing condition. You can use the hydrogen treatment. You can use the optical bleaching, thermal bleaching, etc. But today we don't have so much of time to discuss everything. But on terms of effect of glass composition, I will just highlight. If you have alumina silica glass, it can increase higher ytterbium concentration 2.5 times, larger
Dear
absorption.
Professor Anirban, I'm really sorry to interrupt, but because we had to start late, it's your last 5 minutes, please.
Yeah, sorry, no problem. I'll conclude it within 5 minutes. Yeah, okay. So this absence of central dip, and in case of phosphorus, we can having the prevention of the ytterbium formation, ytterbium 2+ formation, and the reduction of cooperative phenomena. So the limitation in terms of alumina is the enhanced refractive index and higher photodarkening, and in case of phosphorus, it can also increase refractive index and the central dip formation. So what the solution is? The solution is you can use this aluminum phosphorus 1:1, so that you can having the lower refractive index, and as well as you can increase the rare earth incorporation at a higher level. So that is the possible solution. So in that respect, we have also proposed this multi-element fiber where you can increase this phosphorus, ytterbium, zirconium, cerium, aluminium, calcium oxide to get the phase separated preform. And in that phase separated preform, this ytterbium 2+ formation is also possible to stop. And as a result, finally, you will have to get this particular photodarkening induction, reduction of the photodarkening losses compared to the standard fiber. So I am not going through the details of the other part which I planned. I will not go through this, but finally the last slide, what I will just need to show you that what is the application of this laser. You can see this high power fiber laser what we have fabricated is used for the marking. This is the fiber laser based marking system what we actually working for the this type of you can see any type of design is possible to do this, with this fiber laser, and the power level is not very high. This is around 100 to 200 watt. And then finally, this can also be used for the laser cutting. This is the cutting of a 3.5 millimeter thick stainless steel. Okay, so finally, I would like to acknowledge our director, ma'am, and then the colleagues, material characterization facility, my students, funding agency, and my collaborators, Professor Frank Weiss, Professor Fleming, Professor Jointu Shaw, and Dr. Ivan Kasik of IP Czech Republic, and my sir, Dr. Ranjan Sen. Thank you. Thank you for your times and patience.
So thank you very much once again. I think we can take a question if not, thank you very much. Okay, we've got two actually. First to give the student, we've got a student question, Omar, if you don't mind.
Thank you. Actually, my question is not about your presentation, about your research area. As I see in your last article, you are working on SPR sensors. You know that SPR sensors are basically based on the surface plasma resonance. Although chemical and biological analysis can be performed with SPR sensors, this is not looking like useful in reduction changes related to temperature, strain, etc. of chemical or biological materials. Do you think FPG sensors or other optical or electronic sensors are required for an effective and versatile analysis, or are sensors enough? Thank you.
Okay.
Yeah, can you just repeat it, because it was not very clear, but I understand this question is related to the SBS or SRS.
I just want to ask that SPR sensor is enough for chemical or biological materials detection, or we can use for effective and versatile analysis FPG sensors or any other optical or electronic sensors.
Yes, you are right. It is possible. It is possible to use it for these biological samples as well. Yeah, it is true. If you can write me an email regarding this question in details, I can get you back to in more details.
And Omar Zakido, is there another question for you?
Thank you very much. I like your talk. I made many pictures, and it was very detailed. And really shows how sophisticated is your technology. The question is, have you tried, are you doing photonic crystal fibers in your company?
Yes. Actually, it is true that in our division, we are actually working also in the photonic crystal fiber, but the fabrication process, what we are actually using for this photonic crystal fiber is not covered because of the time. How this is fabricated is nothing dealing with this MCBD process. What we do, we generally draw some capillaries of the specific dimensions, and then we stack it as per our design. And after this stacking of these capillaries, we draw it by maintaining a high pressure so that these particular capillaries do not get closed. If I have this one, I can actually show you one picture. I do not know whether I have it or not. No, unfortunately, I do not have that picture. But
I can send you email about that.
Yeah.
I will ask you by email. And I have another very practical question. The two lasers that you showed the video, for cutting the stands and engraving.
Yeah.
Can we purchase them, and what is their approximate cost?
Yeah, actually what you have seen here, these are all our laboratory made products. So we have some industrial collaborator. We fabricate the fiber, we provided the optical engine, and they actually just basically made a box with those things. So if you are interested to buy this thing, we can definitely talk about it, but approximately cost depends upon the power level of the laser. So if you have this only for marking on the this engraving, this will have lower cost, whereas if you have the cutting, then you need higher power. In that case the cost will be higher, but approximately cost as per this marking or engraving is around say 3 to 5 million Indian rupees. 3 to
What
5.
is it in dollars? 3 million rupees.
Okay. Yeah.
In dollars, what is in American dollars? I'm from Texas.
Sorry.
Because I'm from America, Texas, I want to know the cost in US dollars.
Okay. Maybe just a minute. I need to convert it.
Oh, it's funny that you do not remember by memory. 42.50K.
Yeah, no, actually we did not sell it. So it will be approximately just a minute. I can tell you.
Maybe America is under embargo. You do not sell to America.
Maybe.
Maybe that
So
would be a very wise politics, not to sell to America.
It around 7,000 US dollar.
That is not expensive.
37.
27.
Okay, thank you, Professor Anirban.
Thank you very much. Very good talk.
Yeah. Thank you. Thank you.
There's a celebration named Durga Puja, so happy Durga Puja from our team to Calcutta.
Yes. That's why he was late for the online.
As part of our upcoming event, we will be organizing a group photo shot to capture the memorable moments shared during the occasion. So please join us for this.
Break. I'm Aryan Taidi, junior student here at İzmir Institute of Technology. It's an honor and a heartfelt happiness to have you all here at İZPHOTECH 2023. Without further ado, I'm going to introduce our next lecturer. It's my pleasure to introduce Professor Evren Mutlugün, distinguished faculty member in Electrical Electronics Engineering at Abdullah Gül University, Turkey, with a bachelor's in physics from Middle East Technical University and master's and PhD degrees from Bilkent University. Professor Mutlugün's expertise lies in colloidal nanocrystal-based exciton harvesting system for advanced optoelectronics. Recognized with awards such as the 2022 TÜBİTAK Incentive Award and the 2017 Turkish Academy of Sciences Outstanding Young Scientist Award. Professor Mutlugün is a member of the Global Young Academy. Today he will share recent advancements in colloidal nanocrystals, focusing on their applications in color conversion and electroluminescent LEDs. Please join me in welcoming Professor Evren Mutlugün.
All right. Okay, thanks for the introduction and thanks for the invitation, Can Hocam. It's my great pleasure to be here at İYTE. So today I'll be talking about some of our recent work and also some previous works on the colloidal nanocrystals, especially for color conversion and also electroluminescence LEDs. So just in the morning's talk, Serdar Hocam has very nicely explained about the recent Nobel Award. Actually, in the last 5 years, I was always like, okay, this time, but this was the time. So we were all very happy. The community of the quantum dots was very happy about this prestigious award because, I mean, it really deserved recently. Actually, I got the feeling that it would be this time because mRNA was given to the medicine this time. So I was like, if it was given to chemistry, right? So it will be next time. But luckily, this year, the quantum dot was awarded with the Nobel Prize. Yes, there are just 3 of them here, but the community is much larger. Many other people really awarded this, deserve this award, but unfortunately, these only 3 remarkable scientists got the award. So what they did was actually, you know, from the previous talk that Munjiba Wendy was the one who showed the hot injection synthesis in producing these colloidal nanoparticles. But before then, it was Ekim and Bruce who has first shown the size quantization, basically by changing the size. I mean, they have shown that these nanocrystals exhibit quantum-like features. The field of quantum dot is very impressive because the idea is that it is a very clear-cut example of a one-dimensional particle in a box problem in a way. So as we know from the hydrogen atom, so we have the discrete energy levels, and the quantum dots actually resemble these discrete energy levels by nature. So this is why we call them, I will show it later, the artificial atoms, because as the atoms in the periodic table have different properties, you can make up infinitely many different kinds of crystals by making use of these colloidal nanocrystals. That was actually why we call them the artificial atoms. So the size generally we are talking about is on the order of less than 10 nanometers in general. And what we are talking about is confinement, actually, that is due to the discrete energy levels. And what effectively being done is actually modifying the effective band gap, because normally these nanocrystals or semiconductors generally have a certain band gap, but making use of these kind of nanocrystalline sizes, that gives you the room for discrete energy levels, which now you don't have the continuous band structure, but you have the discrete states available. So why they are important? Because, I mean, these kind of changing or engineering the emission wavelength or optoelectronic properties give you very different advantages for different applications, mainly in optoelectronics like LEDs, photovoltaic cells, lasers, or photodetectors. And the quantum dots generally are inorganic materials. As you see in this structure, we have the core and we have the passivating shell as well. And what happens is already what contributes to the photon emission is due to these kind of band alignment in here, but the ligands and the outermost capping agents actually make these quantum dots to be utilized for different applications and make them live, I would say, because, I mean, generally inorganic nanoparticles can only be functionalized by using different ligands so that they can be used for bio applications as well. The good thing about these quantum dots are, apart from the organic molecules, because quantum dots are not the only emitting materials in the nature. We have different sorts of emitting species in the nature, like organics, for example. But the good thing about the quantum dots is that you can tailor the emission by changing either the composition or the size, and also you can get a narrow and symmetric emission profile, which is very critical for some niche applications, definitely for display applications as well. And also the other thing is about their thermal and photostability, as well as the high photoluminescence quantum yield. How we define the quantum yield is that how much photon you absorb and then how much photon you give out of it, and the ratio between them is denoted by the quantum yield, which is also very high in the for the quantum dots. Now, different sorts of structures are available that are emitting in the visible and ultraviolet, and also if you go to different sorts of material set like lead selenide, lead sulfide, you can also reach the infrared edge as well. Well, what we do in our lab is a combination of all in here. We started with the indium phosphide-based quantum dots, which are cadmium-free. The cadmium-based quantum dots are very mature already. We are also making use of them. Different materials like perovskites, there was a question about it in the morning, and also two-dimensional nanoplatelets are also on our focus. So when we say the quantum dots, I use the quantum dot terminology in general, but today I'll be talking about different subsets of nanocrystalline emitting materials as well, like perovskites or carbon dots as well. But the quantum dot is a, let's say, a general terminology to understand about these kind of emitting materials. There are two different modes where you can make light out of these materials. One of them we call the photoluminescence, where we use the higher energetic photons to excite these nanocrystals. And the other one is the electroluminescence. As the name implies, what we do is we drive the current through these materials so that they would give off light. So the idea here is to generate an electron and a hole pair, which we call the exciton. So once we form the exciton by stimulating through the excitation by photon or electrical excitation, then these exciton recombines, the electron and hole recombines, and then it gives off light. So in the morning also we discussed about these kind of spectra a lot. By changing the composition, size, you can tailor the emission band, and which is we are mostly focusing on the visible range. So from blue end to red end, we can tailor the different quantum dots based upon the applications. For example, in this application, we were aiming for high color quality for lighting applications. Like we have the lighting everywhere, so the quality of the lighting is an important figure of merit for different applications, and for different purposes we are trying to mimic the sunlight, which is the natural source of light in our everyday life. But for example, sometimes we are using indoor lighting, and the quality of these indoor lighting can also be manipulated by using these kind of quantum dots. Our recent motivation is more towards the backlighting in this place, because this is a huge platform for nanocrystals to possess their properties as well. And I'm not sure whether quantum dots would get the Nobel Prize if this display application was not in place, because the quantum confinement and everything has been done until now in the last maybe about 50 years is now being flowered, let's say, by making use of these display applications, which I will give you more detail about it. The idea about the quantum dot displays is that we are trying to enhance our color vision for the displays. So the color purity that the nature offers us in the nature is not being possible in the electronic displays as long as you are not using very vivid color sources, which is possible by making use of these quantum dots. Because by making use of the excitation from the blue light and by using the green emitting and red emitting lights, you have the three primary colors to produce all the color spectra, right? And through these color spectra, from these edges, basically, as you go through these edges, your color vision expands enormously. So this is the beauty of the colloidal quantum dots. So the thing is, about 10% of the whole market now is these kind of premium segment displays where it offers better light quality for the audience. And about 2/3 of it, the whole premium market, is now dominated by the quantum dot displays, and it is more than OLED displays as of now. Actually, our work on the quantum dots, my work has started in 2005 when I entered the graduate school at Ülkü University under supervision of Professor Hilmi Volkan Demir. And this was one of the last work actually I completed during my PhD, where we have shown the freestanding very large sheets of quantum dots. It was year 2012 where I graduated from the PhD, and at that time it was 2013 that the first quantum dot display has come out, and it was 2015 that the similar idea of these large area sheets, which we call them quantum dot enhancement films now in the market, which is being sold millions units worldwide annually, which has also come out. So the idea in here is that, so for young audience that I'm talking in here, whatever you are doing, you may be contributing to a very important area in your research. So do not underestimate it at all. So if you look into the worldwide TV unit shipments recently, now we have more quantum dot displays than the organic light emitting diodes. And if you are looking at the recent market trend, now we have the quantum dot mini LEDs, quantum dot OLED, which Samsung kicked in recently by making use of, rather than using a full white OLED, they are using blue OLED together with the quantum dots. And now this is called the QD OLED, and also white OLED is also in the market, and you see the growing trend. The reason why we have the growing trend is not because people are aiming to buy more and more premium TVs, but the cost is also going down. So now what we call the premium segments is still premium, but the cost is getting low, so quantum dots are penetrating more into the market towards the cost utilization. Of course, Samsung is the biggest player in the market, which is having like 1/3 of the whole market in the TV market. But it's not only Samsung or TCL or Hisense or Sony. This is very recent news. For example, Canon is developing now perovskite quantum dot inks for the next generation displays. This is a very recent market. We talked about it. One of the biggest producers of the quantum dots in the market is Nanosys, which has recently been acquired by a Japanese company, Suhoi Chemical. So now, as there is more interest towards the commercialization, there are also big players also coming into the market. So it's not only science that we are looking into, but it's also about the technological advancement that we are trying to get into as well. So this is our company, Nanomi, which was granted the Horizon 2020 at the end of 2020. So what we are doing is actually the similar idea where we utilize quantum dots for better color vision. We do the synthesis, we have the extrusion line. We are making a very large area and very long sheets of quantum dots as well, which also, I'm not sure whether this is viewable with this projector, but on the left-hand side and right-hand side, we have with the quantum dot and without the quantum dot film, and where we see the colors, for example, the tones of the red in here is much better than the pinkish red in here. This is actually what I'm talking about. And as compared with the commercial products, which is the 3M QDEF film is one of the most common one in the market. Our film is having a wider spectral range in here, which would provide a better color vision. So what we do is we are doing the scale up at Nanomi, these kind of materials. We started with the 1 liter flask, which would allow us to produce like 50 grams at once. Actually, now we even have a 20 liter flask that we can upscale it more than 20 times. So, which is really, for our standards, is really impressive, and which has also been seeded by a VC fund this year. So, well, more work on nanocrystals, what we do. I would like to spend the rest of my time on these topics, actually. I'll be talking about the indium phosphide-based quantum dots, carbon dots, perovskites, and also cadselenide zinc sulfide QLED electroluminescent devices. So when I first joined the university about 10 years ago, our focus was more towards understanding the photophysical mechanisms and also optimizing the synthesis roads towards cadmium-free materials. Because now with the regulations and everything, the amount of cadmium is recently reduced to a great extent. However, there's also a trend towards using more environmentally friendly materials like indium phosphides. So by an extensive optimization through using different zinc precursors or reaction temperatures, we were able to achieve high efficiency indium phosphides and also stable materials where we can use them for different color conversion approaches. Well, as of now, we are among the state-of-the-art producers of these materials, actually, which have more than 90% quantum yield. This is for indium phosphide, zinc selenide, zinc selenide sulfide, core alloy shell material, actually. We can have very high volumes through using these materials, and generally for the cadmium selenide-based quantum dots, the full width half maximum in here is even less than 30 nanometer, but this is one of the best in the literature that we can get the quantum dots out, indium phosphide-based quantum dots out by with 38 nanometer full width half maxima, which is amongst the best. We can make large volumes of it, and now we are trying to understanding the emission kinetics and also excitation dependent emission kinetics, which also is very different than the cadselenide based ones, which is also we are trying to understand as of now. One of the issues about the red quantum dots, red indium phosphides, especially for the deep red materials, is about their color purity as well. So one of the things to achieve these kind of materials is that you have to go step by step inclusion of the different precursors. You need to control the thickness of the layers at each time you're making the reaction, which is also troublesome sometimes, especially if you're aiming for high throughput through your synthesis. And for the industry applications, actually, generally, what we are looking into some sort of a one-pot approach where you don't do excess shelling on the materials, but you do it all at once, basically. And the indium phosphide base, especially deep indium phosphide emissions, are generally suffering from the low color purity, and also they require consecutive shelling phases. And this is one of the recent work on the indium phosphide base, which has been published in the Advanced Optical Materials. Still, they have very high quantum yield, but the problem is still they do have more than 50, 60 nanometer full width half maxima, which is not good for these kind of materials. What we did was actually straightforward. We were trying to isolate the core structure by consecutive HF etching, trying to polish, let's say, the structure, trying to get rid of the surface defects by using this, and then continue with the shelling of the layers, which give us very nice results with full width half maxima below 50 nanometer, which gives us the flexibility to tune the emission peak wavelength from the 570s down to 670s down to 650s and everything, and also which give us also more than 65% efficiency. We did an extensive study on the structural measurements as well, and at the end of the day, we were able to show the full color tunability in the red side of the spectra, and with high efficiency, more than 70%, and which has recently, I think yesterday or the day before, it was published in ACS Omega recently. Well, we have a set of infrastructure for fabricating electroluminescent devices as well, and we use these materials to fabricate quantum dot LEDs. And this is not very visible in here, but it's going through the edges in here. So the idea about the color purity is not only about how pure your red is, but it's also, if you go down to these edges, actually, it gives you a huge room for color perception in here as well, which we think also important. Also, for some bioremedy applications, this sort of deep red emission is also very critical. So the next thing I would like to talk about is about the carbon dots. So going from the environmental friendly, one of the other roads towards getting these kind of environmental friendly and also low cost materials is carbon dots. They can be synthesized. You don't need to have a complicated setup, but you can just synthesize it in using an autoclave and an oven easily. And this gives us a room for improvement for mass commercialization as well. It's low cost, and what we did was actually trying to understand, because I mean carbon dots are not regular quantum dot-like structures. The surface functionalization plays a critical role on their emission properties. So what we did was we tried to understand it, and by using sort of amine groups, we were able to achieve high efficiency, and also tunability can also be maintained, and we were able to get very sharp, for the carbon dots, I would say, yellow emission through using these materials as well. This is by the utilization of long-chain octalamine molecules, which acts as an efficient extra shelling layer, because generally these sort of carbon-like molecules are not very stable in different media, but when it comes to our tests, actually at different temperatures as well, going up to 95 degrees, I mean, they did not show a tremendous decrease in their emission characteristic, which is good. We can make very large scale synthesis out of these materials, and it is really at low cost, definitely. Further, we are continuing our work on further increasing the photophysical properties, like extra sulfur doping in here, for example. The idea here was actually whether we can use these materials for electroluminescent devices as well. And what we did, I will talk about the electroluminescence more in detail in here, but actually using these carbon dots into a host matrix, which is acting like a whole injection layer as well. And by changing their ratio in between, we were able to tune the white point that we generate in here. So by systematic tuning of the ratio between these carbon dots and also the host medium, we were able to tune the white emission point through this system as well. Well, you can generate different studies out of these carbon dots that we are trying to understand as of now, with around 60% PL quantum yield for the carbon dots for the blue emission is really nice, and we are looking into more in detail about it. The next thing I would like to talk about these emissive materials is about the perovskite nanocrystals. Perovskite nanocrystals are very easy to synthesize. They have high quantum yield, high absorption coefficient, narrow emission bandwidth. However, they don't have long-term stability, and they're susceptible to environmental conditions, because I mean generally what we use as the perovskites is the cesium, lead, bromides, and iodides. However, as we do for the quantum dots, regular quantum dots, semiconductor quantum dots, you cannot mix and match the color by using these ones, because I mean they have the active anions on the surface. So there's an anion exchange reaction happening so that your material is no longer the same material when you just mix them. So the same here as well for the photoluminescence applications and for versatile use. We were trying to make use of these kind of wax encapsulates, for example, rather than using a very widely used octadecene as the solvent in here. They are using a natural wax, and then by making use of this wax medium, actually you can make dough sort of materials. Together with the Serdar of RGS University, we are working on these kind of different geometries, different versatile applications by making use of these funny shapes as well. And also we can write these quantum dots or perovskites in a very niche way, in a controlled way, by using electrohydrodynamic jet printing rather than using inkjet printing. We are making use of a near field electrohydrodynamic jet printing, which gives us a good room for resolution as well, that we don't need as of now, but this is also possible. And this is one of the stripes actually from our recent work, that you can have very nicely, closely spaced on top of a blue LED platform, and you can get a high efficient white light out of it. Recently, actually, we are working on different sort of sponge-like structures in plasmonics. I mean, take a sugar cube and then immerse it in a PDMS, then just dissolve this sugar, and then you have a platform with full of holes inside. And then we said, okay, why don't we use it for some sort of emissive sponge? Why would we do it? Well, what we can do is we can use it for sensing applications, and we can use it for plasmonics as well. And this is actually one of the work that is ongoing now in our group, which we are trying to push the different sorts of metallic nanoparticles inside, and by controlling the pressure, we are trying to control how much material we can push it, and by making use of these ideas, we can manipulate also the plasmonics in those kind of emissive sponge-like structures. And the same goes for the detection, metal sensing as well. And they are very stable, actually, if you compare it with the just the regular bare medium, which they degrade very fast in temperature. They can resist up to 100 degrees or so in here, and they have very good absorption capacity as well. And this is also one of the things as of now we are doing. This is also possible by, for the inorganics also, they have an extra shell coating where we don't need to coat with the silica or something like that. But for those kind of perovskites, they are very susceptible to environmental conditions that I mentioned just before. So therefore, why don't we use super hydrophobic silica, not coating them, but producing them in situ just after the synthesis with those kind of materials, which you can use it for different applications, which also makes them available to be used for super hydrophobic surfaces as well. Well, as you see in here on glass substrate or aluminum foil or on fabric, actually, you just drop water in here, and then due to the surface hydrophobicity, actually they just get off. So this is also one of the ways that we are trying to preserve the nature of the perovskite in those kind of super hydrophobic silica coating as well. Well, the last but not the least, I would like to talk about QLEDs as well. The terminology for the QLED generally is understood by means of the photoluminescence display applications. So when you go to a techno market and say, I want to buy a QLED, so they would just give you a quantum dot backlit display, which you have the blue LED pumping your green and red quantum dots. But the scientific terminology for the QLEDs is more towards the electroluminescent devices made up of quantum dots. So generally, as you know, we have the cathode and the anode in an organic light emitting diode, and in between you have the hole transport and electron transport agents. And if you have the organic emissive material, then this is called the OLED. But if you have the quantum dots as the emissive media, this is why we call them the QLED. But the structure rest is the same. But depending on the layers that you are using in between, like the hole transport layers, hole injection layers, and electron injection layers, they may be organic. For example, this is organic in here, and this is inorganic in here, one of the most common ways of producing these kind of quantum dot LEDs. But also there may be inverted structures that I'll be also talking about, which you can have, for example, zinc oxide in here, and you can go all the way up as well. This is also possible. So there are many things that you need to be careful about fabricating these devices, because I mean, this is not only about the quantum dot emissive. So quantum dot may be 100% emissive, but when it comes to a film, you cannot preserve the high efficiency. So this is one of the things. The other thing is about the how will you be able to make a very good balance between the electron injection and hole injection, because if there is a misbalance, then the lower one dominates it, right? So this is also one of the things. The other thing is how would you be able to prevent the Förster type energy transfer or Dexter type electron transfer. So these are all actually about the different things that you need to be careful about, and you may be having a different variety of selections that you can manipulate the electronic structures. Okay, I will put this one, I will put this one, but then how about their thicknesses? So this is also important. The mobility is an issue. So there's a real engineering going on through there. So in our lab, we are fortunate enough to have the in-house organic evaporation and metal evaporation inside the glow box system. We have the here, for example, this is how we clean our substrates, and this is the plasma cleaner that we are using in the lab as well to clean the substrates. And also this is inside this glow box where we deposit the quantum dots, for example, using a spin coating. And also in here, in this metal box is a chamber where we can use these masks for our substrates, and we can fabricate devices out of them. This is how it looks inside. And then at the end of the day, we have these kind of different sorts of materials. And we have also customized Hamamatsu quantum yield measurement as well for characterization of our devices. We can pick and select which pixel, this is a passive matrix LED in a way. You can fabricate 6 devices in here, and then you can select which one to excite as well, which is computer aided. And at the end of the day, you can get the different characterization all in one, like the color purity, the current density, luminous flux, quantum efficiency, external quantum efficiency, and everything through our device set. So we make use of our quantum dots, we synthesize our materials, we do our devices, and at the end of the day, we make those kind of electroluminescent devices, blue RGB LEDs actually, and our luminance values that we have been able to demonstrate have more than 100,000 nits with external quantum efficiencies more than 10%. So to give you more idea about this external quantum efficiency is that you know the quantum dots are not favoring the triplet emissions, right? So therefore you have the singlets and you have the triplets. So about more than, I mean, you can only make use of the 25% of the whole photons actually coming out from it, because I mean the rest is the forbidden states. So therefore, through these 25%, we are limited by 25%, and we are trying to not to waste any photons out as well, because I mean there are also internal photon loss mechanisms as well. So therefore, the industry level, the best you can achieve is like more than about 20% or so. So in our lab also we have made use of these equipment infrastructure for trying different nanocomposites as the hole injection. I'll not go into detail in here. And also in a recent effort to use these nanoplatelets, not the quantum dots, but nanoplatelets, because generally the literature is more towards the quantum dots. but we make use of the nanoplatelets in order to have a better device architecture, which have enormous features. I'm not going into detail about the nanoplatelets in here. They are like two-dimensional quantum well structures, which was in 2020, which was published in cover of the Advanced Materials. Actually, this is also one of the pioneering works that we managed. So one of the other things that I'd like to mention is, as compared to the conventional structure, we are using also inverted device architecture for different sorts of on-chip applications. This is common ways to use. And then, however, the literature is still not that mature as compared to the conventional P.PSS, poly-TPD sort of structures. And by engineering the properties that I have recently mentioned about the charge balance, about the thickness composition adjustment, material selection, also passivating the first resonance energy transfer and Auger combination, we are trying to understand better and better about the device architecture. So the regular quantum dot synthesis is like this. You have a vacuum assisted medium. You have the heater, you have the stirrer, right? And you have the injection of the different precursors at different temperatures and times. So this is like cooking in a way. So this is how they get the Nobel Prize. Huh? So then at the end of the day, you have very high emissive quantum dots. So this is like 20 nanometer full width half maximum, and which is around 80% quantum yield, which is like very good, right? So then we use these structures just in here as the emissive layer in here. But in this study, in this recent study, what we did by using sort of a external agents like polyethylenamine and polyethylenamine exolated to improve the charge balance in here. And the idea is how I would be able to inject the carriers better into the quantum dot, and also how would I be able to preserve the structure on its own. So this is about how you can manipulate the energy levels in your structure as well. This is actually what we're trying to do. And by making use of this idea, we were able to employ these kind of PI, and as compared to non-PI case, and by careful optimization, we were able to have 3.5-fold improvement in means of the external quantum efficiency. There's a sweet spot in here. Actually, the rest is about it, but once you have the optimal concentration, you have the good improvement. Not only this one, but also the polydispersity of the zinc oxide that we are using in our structure is also very critical in means of achieving a high color purity as well, because in here, the zinc oxide is the electron injection layer that you start with that one. On top of the ITO, you have the zinc oxide. And even the polydispersity of the zinc oxide is really important to increase the peak luminance and also the external quantum yield. So this is actually how the device looks like after we do the fabrication of the electroluminescent device. And also this is the where actually we are having our corner at. This is the U prime V prime coordinate to give more feeling about the color purity that we have in here. So by careful optimization of both zinc oxide polydispersity and also this PI addition, we were able to show 9-fold enhancement in the peak external quantum efficiency and also the current efficiency as well. So to wrap up everything that we have talked, what we talked about was about the quantum dots, general introduction and historical perspective. I've talked about our recent work and previous work on the indium phosphide-based quantum dots, carbon dots, perovskites, and lastly, I've talked about the mostly the quantum dot LEDs, but our recent work on the inverted quantum dot LEDs, which has been fabricated by addition of the polyethylenamine and also the polydispersity, better polydispersity of the zinc oxide as well. Well, I'd like to acknowledge my group members in here and also the collaborators. Our group is more like a PhD holders club. So we have less students but more postdocs. Recently, we are also inviting applications from the motivated graduate students as well. I'd like to acknowledge also our TÜBİTAK 1004 project, and also our industry cooperation with A.CLaveria. And I'd like to thank you for your attendance. All right. I think the session is open for questions, right?
Very nice talk. I'm very impressed
Thank you.
by all your quality of your laboratory, the way you do things.
Thank you.
One thing I did not understand, these sponges, you template sugar with PDMS, or how you do the sponge, and then you coat it with perovskite or perovskite quantum dots, right?
Yeah.
Then how you sense the metals? That's
a good question. Actually, recently when I deliver a similar kind of talk, everybody's talking about this sponge. So I asked my postdoc actually about 2 days ago. We have to submit this work as soon as possible because it's getting
very
more and more
interesting,
attention, right? So the idea in here is that we were trying to get a versatile platform that we can use for different applications. So how we create the sponge is like you have a sugar cube and you dip it into PDMS, right? And then you get it out, and then you melt the sugar. Then you are left with a sponge like PDMS, but with holes inside, right?
Yeah, I call it inverted. Inverted sugar.
Yeah, negative.
Like my opals yesterday.
Yes,
I showed inverted opal.
Then it is a nice platform that you can use it for many things, right? One of the things is that you need to have an emissive medium so that we put it into a perovskite solution. Then when you take it out, you have the dried perovskite solids on the walls, right? Interior walls and outside of the walls.
Yeah, but they are not quantum dots. This is just solid.
Yes.
Yeah, you can do quantum dots of perovskites and then impregnate them.
Yeah, perovskites. When I say the perovskites, it's a perovskite quantum dot. Okay, this is an emissive medium. We are not doing the synthesis on the cube structure itself. This is you have the perovskite quantum dots, okay, and then you dip it into your solution.
Okay.
This is actually where you have the perovskite solids on the walls, interior walls and outside of the walls, right? This is your platform. Then you can use it for many purposes, right? You can use it as a sensing for different quenchers, for example, right? This is also one of the things you can do. Or you can use it for sensing the plasmonics, because you know that once you have more and more metal nanoparticles around these kind of emissive species, the electromagnetic field around would be different, and then you can observe it through monitoring the exotonic decay, like time-correlated single photon counting, for example.
Beautiful, interesting.
Yeah.
You should publish it because there are many details.
Yeah.
Is it just degrading antimetal? Is it metallic quenching?
Yeah. There are many things ongoing.
Yeah, many things can happen.
Yeah.
But it's very interesting.
Thanks.
Thank you.
Thanks for the question.
Bye.
Any other question?
Okay, then we have more time for the coffee break. Okay, thank you.
Welcome all again. Now it's my pleasure to introduce Dr. Hakan Keskin, who accomplished professional with a strong background in physics and optics. Dr. Keskin completed his PhD in 2023, focusing on the development of a groundbreaking all-fiber optic gyroscope. Since 2016, he has been technical product owner at Roketsan, contributing significantly to interior measurement units, fiber optic gyroscope, and electro-optic systems. As an inventor of a registered national patent on an electro-optic device, Dr. Keskin leads a team at Roketsan, driving the development of cutting-edge interior measurement units. Today, we will share insights to interior navigation systems, emphasizing their importance in GNSS benign environments. Please join me in welcoming Dr. Hakan Keskin to the stage.
First, I would like to thank you for this kindful introduction. It is hard to think which one is harder, giving a talk before the lunch or after lunch. I think you're all a little bit hungry, but after the lunch, if you drink iron, it would be harder, I think. So I would like to give an interactive talk to you. As we proceed, I would ask for your participation. And then I would like to thank you, the organization committee, for inviting me to this great event to meet you such curious minds. Today, I will talk about the inertial navigation systems as a sixth sense of human. As we proceed, I will talk about the details why I called such systems our sixth sense. To continue to my presentation, I would like to know you also. Today, I meet some of you as a second year students, sophomore students, to proceed and well understand each other. I would like to know how many of you are also second year students. Okay. Not much, but good number. Do we have any freshman students? First year? Oh, curious minds. Welcome again. We met some PhD students also. Again, do we have senior student at graduation? Thank you. To continue the introduction part, I would like to talk about my company, Roketsan. Roketsan was established in Ankara in 1888 by the decision of the Defense Industry Executive Committee. We need some defense activities and we need to provide rockets and missiles of Turkey. Our mission is creating value for its stakeholders and employees, as we are, with nation defense solutions in line with our country's goal of becoming a global power. I want to talk about our vision also. We want to be leader of original, reliable, and groundbreaking rocket and missile solutions all over the world for the future of our country. I want to talk about our campuses. Two big campuses are located in Ankara. The first one is in Elmada with a great size of indoor and outdoor facilities. The second one is rising in Lalahan. We have also have a campus in Bilkent and Istanbul Technopark Central. Let's talk about more numbers. As we developing our technology and number of people, the defense needs ranking getting higher and higher every year, and our other accomplishments are also rising. I want to talk about also the personal number because it underlines the importance of the well-educated, great minds. More than half of our personnel is engineer. By engineer, it doesn't mean the basic science are not included. as like me, I'm a physicist and I work as engineer in rocket science. Today, I will start with a small demonstration of 5 senses, which is related to navigation of our target location. And then I will continue to the 6th sense, which is why we need inertial type sensors. This physical phenomenon, inertia, used in inertial measurement unit, and I will give some details about it. Inertial measurement units consist of accelerometers and gyroscope. I will go in details for especially more fun part, which is optics at this point. After these details, we will talk about the sensitivity level of inertial measurement unit. At the end, I will talk about the infrastructure of my company. As I said, I need a interactive talk. At this point, I need a volunteer which will help who will help me on the stage to demonstrate how we will use our senses to navigate. Is there anybody to be volunteer? Can I give a great talk for this incantation? Okay, I will switch to another. Let's go on. Says checking. Is okay. Nice. No, you don't have to go that much. This is enough. I need the other device too. Okay. What will we do here is that we will use each senses, but at each time we will use one of them. Let's start with the easiest one, which is a great sensor that we will all have. I want Kenan to come here to let me complete. I want you come to here, but just using only your eyes, not hearing, not smelling, not touching, or not tasting at all. It will be difficult, I think. Yeah, maybe. Okay. Okay, you can start. Congratulations, it was not that hard. This one was, of course, easy. Let's continue with the hardest one. As you can guess, it is truly difficult. We talk about it too much, but we couldn't find a easily demonstrable way to navigate using tested, but I will leave it to your imagination. Let's proceed with the second easy one. Can you come closer? Because you will close your eyes, but I will make a sound. You will not again use other force. Let's make it a little bit harder. Close your eyes. Let's turn around. And I will make some beep sound like car parking sound, and I want you to come towards me. Beep, beep, beep, beep, beep, beep, beep, beep, beep. Again, give a great applause for Kenan. Nice. It's getting harder and harder. Again, smell, it could be a little bit difficult, but I wore some cologne, but it doesn't affect too much. We can give an example. Our campus's dogs, they were accompanying last night in the visiting room. As I was informed, when they smell the boars, they start barking. So they was trying to find the location of bark. So we can give an example in that point. So we can continue with the last sense, which is touching. Again, I want you to don't use other senses. You will close your eye. When I touch your left shoulder, you will turn left. When I touch your right shoulder, you will turn right. And when I slap your back, you will walk towards. And let's make it a little bit harder again. Let's turn. Let's start. Stop. And that's all. Give an applause again for Kenan. Thank you for your participation. We count down our 5 senses, and in our daily life, we use these senses to navigate. And to list down our classical ways of navigation. Suppose you are a camper or a trekking person, you are going a nature walk time. What type of navigations you can use? Let's write down our lists. Yes, very common one. GPS actually is a brand name for the navigation system. Let's write the more generic one, GNSS. It's Global Navigation Satellite System. GPS is one of them. What other ways you can use to navigate? Of course. Sound waves, of course, like sonar maybe. Yes, what about other natural ways? Moon, of course. An opposite of it. Wind, why not? And I heard first sun and wind, etc. Let's switch colors. Did I miss anything? GNSS, sun. Let's also, we can add stars. Excuse me. And moss. Each of them has a distinctive usage. For example, GNSS, we all have GNSS, GPS in our daily mobile phones. Yes, thank you. What if you are in a tunnel or a underwater device or a vehicle? You cannot use it. Campus. Yes, we got campus. If you have a hill full of iron, the compass will not work. Sound waves, again, it is more useful in the water, but outside it may or may not work, not dependable. Land application. Moon, it will not work in day. Similarly, sun will not work night. Wind, it might not be windy. Stars, what could be the problem? Again, it could be a day or a cloudy day. Most you might be in a desert. Each of them has some usage and disadvantages, so we cannot rely on them all the time. This could be a huge problem. Start to survive in a nature. So we need to develop other senses. Is there any Spider-Man among us so that we can use our spider senses? I don't think so. Or any Jedi? I would love to. Nothing will help us and any other unnatural skills. When I see you, I saw engineers and scientists. So we need to do some math. We need to use physics in order to develop our six senses. Let's start with a brief definition of inertia. Inertia is the tendency of objects in motion to stay in motion and objects at rest to stay at rest. We all familiar with this concept. We will use this phenomena. If there is a net force acting on a body is zero, we will talk about the inertia. So that we can use inertia physics to develop navigational systems. In order to develop all the time reliable systems. Inertial navigation, you can think of it as an intrinsic characteristic. Without using any information outside, like I tap shoulder or the light from sun or wind, magnetic field, there will be no interaction with the outside. Imagine you are like you are placed in a black box. Let's talk about the inertial measurement unit. In order to give direction or define your position in the three-dimensional space, we need three locations, x, y, z, and in order to define your position and direction, we need other three angles, let's say Euler angles. So that we need a 6 degree of freedom. Here, accelerometers and gyroscope, which are inertial devices, comes to our help. Accelerometers measures acceleration using, again, inertia, and gyroscope measures gyro, which is rotation. And then the output of these six devices combined using processors, and the output is given to upper systems. Here are the examples of inertial measurement units that are developed and produced in Roketsan, and all around the world there are lots of companies who are trying to develop and increase their sensitivities. Let's start with the less fun part, accelerometers, because they use mechanical background. Simply, they measure linear acceleration using second law of motion, that was Newton's formula. The output is given in terms of acceleration units, which could be g, gravitational, or meter per second square. How accelerometer works? When we have a spring, a mass system inside the box, if it is at the rest position, the mass will stay in the middle position, let's say. Here. If you want to accelerate the outer box towards any direction, the inertia will make the mass at the center, but the outer box will try to move. The relative position will give me the accelerometer level. It will be the same for the gravitation. If the outer box placed on a table, the inner mass will be pulled down, and the springs simply will be stretched or compressed. The displacement will give again the acceleration. We can again we can make an experiment. Let's say this is the green box pen. What will happen when I drop the accelerometer like here? Imagine there's a mass inside, also the spring. What will be measured? Here I am holding it and it measures gravitation, but when I drop it while traveling, in your opinion, what will be measured? Any idea? Correct. Because the inner mass and the outer box travel together, there won't spring force inside, so that they will not measure anything. In order to increase the sensitivity of the device, okay, I will switch again. We use magnetic force to balance the mass inside. The level of the magnetic field give you the acceleration. Let's continue with the more fun part, gyroscopes. Gyroscopes are simply the angular rate measurement device. Gyro comes from the angular rate. And we can talk about optical gyroscope and mechanical gyroscopes. Optical gyroscopes use the principle of second effect, which I will explain in detail. And mechanical gyros uses Coriolis force or angular momentum. What is Sagnac effect? Let's think these red lines as a resonator or optical path of light. At the beginning, light enters from starting point. Here is a conjunction point, like a coupler. The light divided into two. One portion of light travels counterclockwise, and one portion of light counterclockwise. There is no rotation. The lights clockwise and counterclockwise travels together and reach endpoint at the same time. But if there is a rotation during this process, the counterclockwise light arrives earlier, and the counterclockwise light needs more time to achieve ending point. This difference is related to omega, which is angular rate, which is sine effect. At the bottom, we have some examples of gyroscope. The first three was mechanical gyroscope, and the last two optical ones. Let's continue with the optical ones together. The first one, optical gyroscope, as a ring laser gyroscope, and the second one is fiber optic gyroscope. Both of them are again designed, developed, and produced in rockets. The sine effect formula given at the bottom. Here we have our input as an angular rate and output as a phase. The phase difference that I talked in the optical path length. The relation given by scale factor, which is the length of the optical path, diameter of the optical path, and it related also the light wavelength of the light that I use. Let's go into details furthermore. For the ring laser gyroscope, we may have a rectangular or square resonator. In order to have a resonator, we need a closed loop consisting of 3 or more highly reflected mirrors. The third mirror has less reflection in order to have some coupling outside, so that we can measure the clockwise and counterclockwise beams. Inside this cavity, for the ring laser gyroscope, we use helium neon lasers. In order to have a very narrow bandwidth, it is a great device to be used. Using these anodes and cathodes, we apply high voltages to excite our gain medium, and resulting lasers given at the output, again combined using a prism, which will result in interference. Depending on the amplitude of the rotation, these interference patterns move horizontally. When I count them, I can calculate the rotation rate amplitude. This is the resulting ring laser gyroscope that is produced in rockets. It is more complicated than it looks because it also has some mechanical parts, very high precision manufacturing processes. Actually, it is, I can say that it is hard to produce but easy to design. Let's continue with the ring laser gyroscope. In order to have a high levels of sensitivity, we need to start with some simulations. We use ZMAX or SPOs to develop our systems. I would like to advise you to develop your skills using such softwares. For example, here we are simulating the beam profile across the ring laser resonator, and again interference pattern is observed at the output mirror. For the fiber optic gyroscope, it is a little bit complicated but more easy to produce. Again, we need a light source. In our application, we use amplified spontaneous emission light source consisting of laser. As you can see, this is a very complex system, including both electronics and optics. When we try to produce inertial measurement unit. Other disciplines are also included. Let's start with the light source. As I said earlier, I use a amplified spontaneous emission source. Again, we need to simulate to get a better performance at the end. Starting with a laser diode, the output is converted to an amplified spontaneous emission source using an erbium doped active fiber. Here we have the gain and loss of the erbium doped fiber. At the right top section, we have this output spectrum that is produced by this output. It's okay. Clear. Not that clear. Okay. At the right bottom section, we have a in-house produced AC source. Again, consisting of laser diode and other optical components. These are produced by photonic engineers among us. I can additionally say that we have a collaboration with a university in Turkey to develop a single mode laser diode. Let's proceed with the MIOC. It stands for Multifunctional Integrated Optical Circuit. It's a long word, but it deserves its name. It's composed of a polarizer, coupler, and a modulator. So we can say it's a multifunction. We like this component a lot because it combines multifunction in a small dimension. When we look at the schematic of this MIOC, we see that fiber is coupled to our substrate using a mechanical structure, and then it is directed to modulator using a Y-branch coupler-like structure, and then light modulated using electro-optic modulator. Again, we give very importance to collaboration with our institutes and universities. And again, we develop our MOS. We want to develop MOS using collaboration with institutes and universities. Let's proceed with the fiber coil. We use PM fiber, which is polarization maintaining fiber. The input beam preserves its polarization characteristic using this kind of fibers. Why we use is this kind of fiber related to environmental effect. The effects of temperature or other environmental effects suppressed using this kind of fibers. Additional way to suppress temperature effect using a symmetrical methods. Let's say we have a temperature change at this point of the coil. But when I wind this structure symmetrically, if the temperature perturbation affect the symmetrical way, they will cancel out. If I increase the symmetry even more, this effect even less. The resulting fiber coil looks like this, which is wound in rocket science. Again, collaboration comes to our mind. We are at developing stage of a PM fiber in Turkey. At the end of our fiber optic gyroscope, we have a photodetector. It's an again combined structure consisting of high-speed photodetector and field effect transistor. We are using a very low optical power, and again, less optical power means less electrical signal. So we need to amplify using a circuit that is shown at the bottom. These are the pictures that are developed inside Roketsan, and we are developing a collaboration to produce a high sensitivity special designed PIMFET with a company in Turkey again. At the end, we combine all of these subsystems together to produce our AMUs, and at the end of the production line, we test and see their performance. The result is satisfactory even Jedi Masters. We have now our inertial measurement unit. We need to define how well it is and how can we be used depending on the application. Depending on the application level, starting from industrial, like in our mobile phones, sensitivity level requirement depends. For high level application, we call strategic level IMUs. The numbers getting smaller and smaller. Like in the photonics, smaller is the better. For both accelerometer and gyroscope, many applications require such systems, starting from our daily life to space applications. As a defense company, we need to develop our devices by ourselves in case of any disturbance in the procurement department. So we start from raw materials to develop our sub-optical components like ring laser gyroscope or in quartz accelerometers. We develop our mirrors ourselves. We design our mirrors, prisms, and optical windows and other lenses by ourselves and produce ourselves. At the end of the line, we have our production capabilities, which is consisting of fiber coil winding. During this winding process, we use some special glues. After completing the coil, we cure these glues special ovens. At the assembly line, we complete our production of inertial measurement unit. At the end, we test them to how well they will perform. These are the examples of inertial measurements are produced in Roketsan. Depending on application, they differ their mechanical structure, electrical structure, and again sensor sensitivity. Let's compare basic sensor sensitivity that are developed in Roketsan. Turna stands for Turkish Navigation, and starting from tactical grade, we have navigation grade inertial measurements also. The first parameter that we compare the measurement range, that is capability to measure how much angular rate input can be measured. One of the most critical parameters is bias repeatability. Bias is like an error at the output when there is no input at all. Let's say it is in the steady state, but it still produces some output. This is our one of the basic errors. As the numbers get smaller, the sensitivity increases. Other important parameter that I want to focus on is the angular random walk for gyroscope. It is like a noise parameter of our devices. Again, it gets even smaller for higher and higher level sensitivity application. It is similar for the accelerometer also. Again, measurement range, how much G, how much acceleration can be measured, and the bias repeatability without no acceleration. At the end, we have the random walk of our accelerometer, which is the noise parameter. At the end, I would like to remind you all that inertia very critical physical phenomena, and it is good for our sensors, not for people. Thank you for your listening.
Are there any questions?
Thank you. Excuse me. We are.
My question is about where would these devices would be used exactly? For example, do we just take the devices and take it to the field, or do we put in a plane or a flying?
For military application, we use it for every devices that we produce. In our daily life, it is in your mobile phone again. When you rotate your mobile phone, it detects its rotation itself. Again, when you have a drone inside the room, it will use its gyroscope inside. When you have a submarine system, there is no GPS, as we talked earlier. It had to be used at that application also.
I understand.
For example, the new cars that are developed, they can travel by themselves, so that they need such systems also.
Okay. And what is the scale of these devices? Do you show them isolated from any other devices we can compare them to as per size?
I want to put mechanical size. The less sensitive that I show, about 15 centimeters long, for example.
Okay, thank you.
Around here. Thank you for the question.
Any other questions? May I ask one?
Of course.
What does the random walk in your chart mean? I didn't really get it.
Each sensor has its own error. When I my hand on Kenan's shoulder, there might be a misplacement, so that it may be directed to wrong direction. At each step, it even increases even more. This is the noise parameter for each device.
Thank you.
Thank you for the question.
Are there any other questions? I guess not.
Thank you for your attention.
Thank you, Dr. Keskin, for this very interesting and interactive presentation. Now it's my honor to introduce Dr. Serap Yiğen, distinguished physicist and design architect at Vestel Electronics R&D Center. Dr. Yiğen's journey in applied physics, including a TÜBİTAK-supported phase, has led her to pivotal role in technology development at Vestel. Today, she will share insights on emerging display technologies, exploring innovations, key features, and challenges in evolving landscape. Join me in welcoming Dr. Serap Yiğen to illuminate the paths of visual experience.
So hi everyone, thank you for the invitation and thanks for the introduction. So I'm from Vestel Optical Design Team. So today I would like to talk. And I know probably last 2 days you listen a lot about display technologies, maybe optical materials. So my point is to give you a general idea about the industrial side, actually, industrial perspective of the emerging display technologies. So here's my outline. At first, I would like to introduce our team in RD department, Optical System Design Group at Vestel. And after that, I would like to mention what does an optical designer do in a design. Students here in photonics and physics, maybe in engineering department, and you are just shaping your career. You might be interested in display technology, or you might become a display designer at some point. So I'd like to give you a taste of what you will be dealing with the industry side. And after that, I will introduce display design and backlight unit, because I will be using this term backlight unit, and I want you to know what it means. And after that, we will look at the display technology timeline and the history and where we are at now and the industry side and the future prospects of the industry. So here is our team. We are located at Vestel Electronics Factory in Manisa, Organizasyonel Bölge. We are responsible for designing the backlight units for all the display products. The group is first established in 2007, and we are mostly made of physicists. We are 22 physicists right now. 3 of them are PhDs. We have PhD candidates, we have master's degree, we have master candidates, and we also have bachelor degrees. So we have physicists, also we have physics engineering graduate, we also have electric and electronics engineers. We have colleagues who has a master's degree in photonics, but we don't have graduates yet. So maybe one of you will, or some of you will become our colleagues in the future. So as I said, we are dealing with the design of the backlight unit of the displays, and we also run some research project that I will mention a little bit in my talk as well. So what do we do as a group? As I said, we are responsible for the design of all the backlight units of the TV products or visual solutions product. Visual solutions or digital signage products means the displays that are not TV. So what could be the displays that are not TV? It could be your information displays that you see, or LED walls you see in the shopping malls, or even if you have a smart board in the classrooms, this will be your non-TV product, visual solutions product. So I'm in the team for visual solution products, design of the visual solutions products. And as a team, as we are responsible for all the design of the displays, we are also responsible for choosing the optical components based on the project and approving of these optical components. So what are the components? Are LED bars, optical films, etc. We are all responsible for testing and approving these products. Apart from that, except for that, we are also doing research and development of advanced display technologies. So we are directing technology development projects, and one of my responsibility in the team is to manage these technology development projects and to lead the academic industry participated joint projects. So if you have any idea or projects, I would be happy to talk to you after this talk. And after that, we also provide support for the display production line in the electronics factory. So what are our research interests? And I'm sure our research interests are very matching with your research interests here. So I'm sure we can find some common ground to make some research projects, and our aim is to take your research that you do in your laboratory and we make it in the mass production in a product in real life application. So what are we interested? We are interested in doing displays. So we are interested all types of novel optical materials or process for this manufacturing techniques for these materials. So we are interested in making energy efficient displays. As you may know, sustainability is the biggest issue right now in the world. So we need the products that consumes low power and less electricity, and we also need some productions for the sustainable materials. And we also want to do displays with white color gamut. You may have heard this term or you may not. I'm going to introduce what it means. So white color gamut means you have beautiful colors on your screen. You have beautiful green, beautiful red on the screen. So we want to have high brightness, high contrast, and so on. So if you have any materials, any optical materials or process or manufacturing techniques that will lead us to have this display, so we are very, very interested. And we are also interested in emerging technologies for different display types. One of them is micro LEDs and mini LEDs. And we are interested also augmented reality or AR, VR technologies. We are interested in transparent displays. We make also automotive displays as well. So other than that, we are interested in video engineering or picture quality or image processing of the research areas. So we can find some common ground, as I said, and find some TÜBİTAK project and work together. So as I said, our team is made up of optical designers, and what an optical designer means. So if you become an optical designer at some point, and if you design a display, so just let me give you just to give you an idea what you will be dealing with. So basically, you will, if you want to make a display, you will be designing the backlight unit of it. So your purpose is to have nice color on the screen. So I have over here just the cartoon of our human eye. So I'm not a biologist, so I'm not good at biology. I can't explain the details of all the cell structure, but our eyes can perceive colors very, very nicely. So if you look at the image over here, at the back of our retina, we have some cells, like receptor cells. These are called cones and rods. And these cells are responsible for the color perception of the eye. So our eyes are actually very good at receiving the colors. So if you look at the spectrum over here, in the visible range, we can see all nice colors. So if you become an optical designer at some point, your ultimate goal is to reproduce these colors as much as you can on a display. So there is a way to express these colors. So if you look over here, we have a CIE color coordinate system. So if you become an optical designer, this will be one of your best friends, because you will be dealing with this a lot. If you do lighting application or display application, the color quality will be expressed with this coordinate system. So if you look at inside, you have this horseshoe shaped structure. So this encapsulates all the colors that a human eye can perceive. So if you make a display or LED, a lighting product, you can create a green color on this here, and it will have a specific coordinates, so you can express your colors in numbers. So it will have a specific CIE X coordinate and Y coordinate. So if you, let's say, have a display that produces green color over here and red wavelength over here and blue, and if you put these three dots, you make a triangle. That means your display can generate all the colors that is inside this triangle. So this is called the color gamut of the display or color gamut of the lighting applications that you have. So if you make a wider triangle, that means you can produce more colors. So there are ways to make this. You can use spatial LED phosphors, I will mention in a second, or you can use quantum dots that will give you more pure colors like red, green, and blue. So you will have a white color gamut display that I was mentioning just a second ago. So if you have a white color display, you don't have to be an expert. If you just walk into a store and if you look at different displays, and you will see that displays produces different colors. The red is not same for all, green is not same for all. As you see over, I don't know if it can be seen over here, but some of the displays, like quantum dot based displays, for instance, it will produce better greens, better reds for the display. So yeah, if you become an optical designer, your goal is to make this triangle as large as you can and have nice colors on the screen. And of course, you want to have a higher brightness, and you want to have a higher contrast, and so on. So the other thing you will be dealing with is as I said, the optical nanomaterials and the characterization techniques. Sometimes within our team, we have to look at our optical components. For instance, optical films, we need to analyze them, we need to characterize them. So we use nanofabrication techniques to, to characterize them and look at the structures. So you need to have an expertise in optical, you will gain expertise in optical materials and the characterization techniques. And you will be also learning different display panel technologies if you become an optical. It is actually the illumination that illuminates your screen. So if you, let's say, take a TV like this, and if you layer down the TV from top to bottom, you will have different components, and each components will have many, many layers inside them. So the black side on the top of the screen, the black material, black components, is the liquid crystal panel. So if you remove this from your screen, if you take the liquid crystal display, which also produce all the images on the screen, so if you remove this, you will be left with the backlight unit. Okay? So for the liquid crystal panel, I will be talking more details in my next slide. But basically, if you look at over here, it is composed of many, many layers. You have the liquid crystal cells sandwiched in between, and you have ITOs, which is your TFT thin film transistors to run all the pixels, and you have the color filters, and you can see these color filters on a TV or on your laptop. If you can see by eye, I mean, if you go with your cell phone and then if you just zoom it with your camera, you will be able to see this red, green, and blue pixels on the cell. So I will be talking about how it works in a second, but as I said, if you remove this liquid crystal panel, whatever left behind is your backlight unit. So as an optical designer, your first objective is to design your backlight unit, or sometimes we call it blue. So for this one, in the backlight unit, first you need the illumination and you need the light in the system. In the past, we used to have fluorescent lamp, but after LED is discovered, we now use LEDs as the illuminator for the backlight unit. And after the LEDs, you have a bunch of optical films, and this is your responsibility as well to choose the proper optical films for your design. So here you have for instance, the diffuser plate or diffuser sheet that helps you to diffuse the light that comes from the LEDs. Because from LEDs, you have different LEDs in the backlight, and it emits some light it emits some light, and you have to take this light on the panel, and you have to have a homogeneous distribution of the light in the backlight. So to make it homogeneous, you have to scatter your light. You also have to gain them and then direct it to your LC cell. So you use prism sheet and other types of optical films to do so. Basically, for instance, if you wanna make a display which has a brightness of, let's say, 300 nit. Nit is the general unit we use for the brightness per unit area. You have to have at least 6,000 nit brightness in the back of the cell, because the cell has roughly transmissions of 5%. And it depends on which cell or which model that you use. So you need to adjust and make your backlight unit accordingly so that you will have your target brightness at the end of the screen. So for backlight units, we have different designs. We have a direct LED or DLED, or we have edged LED design. So for direct LED, basically you have your LEDs like this, and you distribute them in the back panel of your display. So this is called direct LED because the light is directly coming from the back. And the other type is edge LED, and for this one, you put your LEDs on the sides. You could put you in the horizontally low, horizontally top, or verticals. So the light will be coming from the sides, but you need to use a specific optical film to direct this light to your liquid crystal. So this is a different design. With this one, you can have slimmer displays. With this one, you can have different optical distance, different thickness for the displays. So for DLED type, we have different type of lens. So if you design a display, you have to choose either, let's say, top emitting or side emitting lens on the LEDs, and you need to design this as well, so that you will have a nice distribution of light. So you have to choose the LED package or phosphor type. So the phosphor type, if you look at over here, as you know, LED emits like a, if you look at the LEDs closer, you have this yellowish coating on top. This is a white phosphor we call, and this phosphor converts to blue light to white light. But this one is not super good, but it's cheap, so it's mostly used in the displays. Because if you look at over here, the spectrum of this LED is not so good, because if you want to have a nice white color gamut display, you need to have pure colors coming from your backlight unit, like the pure red, pure green, pure blue. So over here we don't have this, so you can't have a white color gamut display by using this type of LEDs. Instead, you will have just a standard gamut display. You can make a standard gamut display with this one. If you want to reach a white color gamut and have nice colors on your display, you can use a different type of phosphor, which is KSF phosphor we call. And as you can see here, compared to this one, you have the blue peak, green peak, and also you have this red pink here. So you can have more pure colors on the screen. And the best way, the better way is to make a quantum dot display. So you can have directly blue LEDs in the backlight. The blue LEDs will illuminate your quantum dot film, and you will have nice colors on your display. So for white color gamut, as I said, quantum dot and KSF phosphor will be the solution. But for white phosphor, you will have only standard gamut display. But in the industry, we use this in the most of the panels because it's cheap and people want to buy, displays that are okay. So we do panels with this chip. So on the top of the backlight unit, we have the liquid crystal display. So basically, as I showed before, the liquid crystal cell has many layers. So you have the liquid crystal sandwiched in between. You have the color filter that gives the colors on the screen, that makes all the image on the screen. So your backlight has the white color, and with this color filter, you will have red, green, blue, or mix of them, and you will produce any colors on the screen. So the idea here, you have, of course, the polarizers, because the working principle is based on the polarization of light. So you have these thin film transistors on each pixel. So if you make them on and off, you can change the alignment of this liquid crystal. So that is how you let the light out or close them, so you don't have any light coming out from the pixel. So there are different types. We have the in-plane switching type. So the liquid crystals are aligned like this. So if you make it on, they will align themselves, so they will let the light go through the pixel. Or we have the vertical alignment type of cells. So the liquid crystals are aligned vertically, and then if you apply the voltage, they will open and let the light out. So one of the fun way to know if you have the VA type or IPS type LCD on your screen, you can just poke on the screen when the backlight is on, but the LCD is off. If you poke on it, if you have a vertically aligned LCD type, with the pressure you will open the liquid crystals, and there will be some light leakage through that, and you can see the backlight, the white color. If you move your finger around, the white light will be going around. So that's way you can know that you have a vertically aligned LCD on your panel. So that is how the liquid crystal display works. And because of the time, I can't go in very details for this display design, because there's a lot of details how we characterize the displays. There's a measurement techniques that we use, and so on. So I can't cover it everything, but of course, if you're interested, we can always talk. Or if you come to Vestal as an intern or maybe as a full-time job, you will be learning all these details for sure. So this is the idea of the display design, the backlight unit. So if you want to look the current status of the industry, I will just mention the history of the displays right now. So the first display, we have the cathode ray tube. I don't know if you ever seen it or if you remember it. The TVs used to like this, a big box, and it's made of with a cathode ray tube. And with this one, we have this bulky structure, and then after that we have the plasma TVs, which is a different technology. And after that, we moved on the LCD after the discovery of liquid crystal displays, or TVs or displays become slimmer and nicer. So LCD sometimes used, and I have to tell you that the first TV wasn't cheap, because it's always like this. When the technology evolves, the first product is expensive, and when you make the materials and manufacture process cheaper, it will become cheaper as well. So when they first produces this cathode ray tube television in 1934, it cost like $8,000 in today's money. Okay. So after that, we have the liquid crystal displays. It was invented in 1968, and the first display or TV product that has a liquid crystal display was produced 1990. So it is again a development period of time is like 22 years. And after that, we have the quantum dots, which was first invented in 1980s, and the first display or TV product that utilized the quantum dots was produced in 2013. So it's again a development period of over 30 years. And again, we have the organic light emitting diode, which was first invented in 1987. And the first OLED TV or organic light emitting diode TV was produced in 2008, and it was over 20 years. So right now, we have a new technology called micro LED. It was first introduced in 2000, and the first 55-inch TV made of micro LEDs was introduced in 2012, and we also have others in 2018 and 19. I will show you in my next slides. So as you can see here, the development period is getting shorter and shorter by time, because that is normal. In the past, we don't have these complicated manufacturing techniques. We didn't have this research infrastructures and so on. So the development period is getting shorter and shorter. That means the research that you do right now in your lab would be in short time will be maybe applied in the industry as an application. So that is something to point out. But as I said, the first production is always expensive. As I said, the TV for the first cathode ray tube TV was $8,000 in today's money. And the micro LED TV that is produced in 2018, I guess, and it's costing over $100,000. So always the first one are expensive, because there's a manufacturing cost is expensive, the materials is expensive, but by time, like the TVs, in the past, the LCD TVs were very expensive, and when the technology evolves, it becomes common and it became cheaper and cheaper, so everybody could buy it. Organic materials or the quantum dot materials are produced and manufactured more, and so it is used in industry more. So we are able to get QLED or OLED TVs in the market. So if you just compare with those, and as you can guess, of course, the QLED, quantum dot, or organic light emitting diode displays are best in this sense, because the brightness are good, their contrast ratio is good, and most importantly, their color reproduction is amazing. If you look at if you go in a store, if you look at a QLED or OLED TV, and you will see difference just by looking at the colors. And energy efficiency, I said the only drawback right now is LCD is affordable, but the other technologies are expensive. That should be the one. So they have actually, again, organic light emitting diodes, but here the organic light emitting diodes are only producing blue colors, and they have the quantum dot as the color conversion layer. So this is called QOLED, and it's a new trend in the market. So except for those, we have mini LEDs and micro LEDs, and as you know, LED also is evolving as a technology. They are becoming smaller and smaller. So we have mini LED displays where we have many tiny LEDs in the backlight unit. The new technology, the newest one, is micro LED, and this is the newest one. And we believe that in the future, the micro LED will be the feature of the display technology, as today LCD. So as instead of LCD, in the future, micro LED will be common and it will be used in the display technology. But we have still time for that because, as I said before, they are still too expensive. So if we look at the LED types over here, we have these traditional LEDs that we actually use in the LCD or LED panels. So their size is bigger, and we use this in the backlight units, and we use in the lightning application. So right now we are going to smaller size. They are getting smaller and smaller. We have mini LEDs, and mini LEDs also, they are also used in display design, and we also use it in LED wall product that I will mention in a second. And if you go further in size, we have micro LEDs, and as I said, this will be the feature of the technology. Micro LED will be used in everyday product, from your cell phone to tablet or display, the TV, affordable. So let me introduce new technologies, just to give you an idea what we have right now. And one of them is called LED wall. And as a visual solution team at Vestel, this is one of our responsibility to design and produce LED walls. And basically, you don't have a backlight over here. You have these LEDs. They're like you put them in like a matrix form, and you give this matrix-like structure. So first you have the pixel as your LEDs, and the distance between the LEDs decides the pitch size or LED pixel size for LED wall. So this is becoming smaller and smaller right now. This is over here, I put it as an example, 4mm pixel pitch, but this is huge right now, because right now in the industry we are going in the smaller and smaller size. So the pitch size is going like the 0.6mm and down. So if you bring all these LEDs together, you get the LED module, let's say 32 to 32 LEDs, and you can take these modules and you can combine it with the other modules, and you can make a big screen. And the good thing about LED walls, it gives you the flexibility in size and shape. So you can bring as many modules as you want, and you can make your size bigger and bigger. So you can get high brightness, and you can get a wide viewing angle as well. So you might have seen these LED walls, I don't know, maybe in shopping malls or in maybe in the soccer games or in the back. But if you have never seen it, I'm sure you probably heard this gigantic sphere sitting in the middle of Las Vegas. So this is the LED wall. So this is made of like million of LEDs together, and it's made in a sphere shape, and you can watch the videos about this on YouTube. So this is the largest LED wall in the world right now. So what are the challenges with this LED wall? Okay, we produce them, but there are still challenges there because they're expensive. And the reason they are expensive right now, there's a demand in the market to have a smaller pitch size, because if you have a large distance between your LEDs and you can't look at it in a closer sight, you have to go, at a distance to see the whole image. But if you make your pitch size smaller and smaller, it will give you higher resolution, and it will be more like a TV-like product in the system. But if you make them smaller, the problem is with the manufacturing process is getting expensive. So this is one of the challenges right now, to make it smaller pitch size and make the cost effective. And this is the pixelation effect, is the thing that I just mentioned. You have to put a viewing distance depending on the pitch size. Okay, so the other technology that I mentioned, one of the emerging technologies, is micro LED. And as I mentioned before, this has many advantages over the current technology. So if you look at over here, LCD, the current one, we have the largest market share. It has the lowest cost, and the technology is very mature right now. You can produce it very easily. And we have the organic light emitting diode display or quantum dot display. So for here, if you compare micro LED with this technology, it has more advantages. Of course, it has a higher brightness, it has a higher pixel density, it has a faster refresh rate, and so on. But the only drawback is right now is the cost in the market. So we need time for the technology to evolve. But we predict that we can predict the market share by year. If you look at over here, by 2025, micro LED will be dominant in most of the applications like smartphones, tablets, and TVs, and so on. So it will enter the market more, and you will be seeing it a lot more. Right now, as I mentioned before, there is a few companies produce micro LED TVs, and this is one of them. It's called the Wall. I think it was made by Samsung. But as I said, now it's very expensive. Like the first TV in the history is costing over $100,000, but in the future, it will be cheaper. So the challenges with this technology, as I said, it's the cost, and the main cost is coming from the manufacturing challenges. Because for these displays, the manufacturing process is complicated. You have all these micro LEDs, and to make the screen, you have like 1,000 million of them, and you have to pick them by one, and you have to put them in a precise location. So this mass transfer is kind of difficult. You can make it, but it takes time, or it's very, very expensive. So if you look at the literature right now, you will see a lot of manuscripts, papers about micro LED technology, and they are mostly focusing on the transfer technology of micro LEDs. There are a few techniques that is used right now. Picking and placing is one of them. But as I said, for the mass production, it is costly and it takes time. That's why if you make a display like this, it will cost you a fortune in today's technology. But in meantime, like other technologies, LCD was at some point it was difficult, but it was made and cheaper and cheaper. Now we can see it in everyday in our homes and so on. And micro LED will become like this at some point. So if maybe if you're interested, maybe this is a research topic as well. You can do your PhD or master's in micro LEDs. There is a different perspective on this technology. You can work on the back plane. You can directly work on the producing LEDs, or you can produce the LEDs like the blue LEDs, and you need to put the color conversion layer like quantum dust to have a nicer color on the display. So that will be another research topic for your studies. And lastly, I have one more technology that I would like to mention. This is not actually new, but I like to mention it just to give you an idea. Maybe you will be interested in this as well. So this is called electronic ink or electronic paper display. And as I said, this is not a new technology. Actually, this was in the market for some time. If you ever had this ebook reader, Kindle type of thing, this technology is based on this electronic ink or e-ink technology. So this is like a paper-like display. So you have, if you look at the ebook, you see that it's like a paper, and everything you see on the paper, it's reproduced on the screen. So this technology is good because you don't have a backlight unit for this system. This is what we call is a reflective type of display. So actually, you don't have a backlight in the back, but it is illuminated with the ambient light. So it takes the ambient light to reflect and makes the images for you on the screen. And the good side of this, if you don't have a backlight unit, there is no power consumption. That's perfect, right? Zero power consumption. But the drawback is you need the ambient light, so you can't use it in the dark. So if you make a TV like this, and if it is dark, so you have to go to bed and sleep in the displays like in TV or other products, because we want to make a low power consumption displays. As I mentioned before, the sustainability is the biggest issue right now. So if you make let's say advertisement board on the street with this technology, it's better than the other technologies because it will consume no power. That's perfect. Okay. So this is the idea how it works. If you look at over here, you have this little microcapsule that encapsulates electronic ink. So the name comes from their electronic ink or electronic paper display. So the idea, these microcapsules are put in between two electrodes, and if you apply a voltage, and you will be taking, let's say, negatively charged white ones on the top and positively charged ones in the back. So back and forth, you can create this image on the screen. So this is, of course, for Kindle type of application. For ebook reader, you can have white and black colors on the screen, so you can see the writings and the refresh rate, but the refreshment rate will be really slow for this one. So if you remove the voltage, it has to come back and so on. You don't have the same refresh rate as the regular display. So this is one topic that you can also think about. So this was first introduced, as I said, in the ebook readers as a black and white. But now, right now, especially in China, many companies are producing different electronic inks with different colors. So you can produce actually colorful image on this displays. And this is one of the example, actually, one of the technology fair in this year. They were showcasing their products. As you see over here, in, let's say you walk into a shopping mall or market, you have these displays made of electronic ink technology. So you have different colors, and if you just, apply a little voltage, and then you have this image on the screen. But from here, you can use this as I said, for the advertisement board or other things. But the question is, can we apply this as a display? Like, can we animate any image on this? Like, can you play a video like in a TV? So that is a challenging question. And recently, a Chinese company, TCL, introduced that new tablet, and they are claiming that they are using this electronic ink technology in the tablet, and they can animate the image on the screen. So you can play videos. It's like a real tablet. You can play videos and so on. But over here, of course, this is quite new and it needs to develop. It's also a research topic. So the question is, can we take this technology and make in, let's say, a TV product? Because if you use this as a TV, let's say, or any other panels, you have to first create all the colors. And the good side is it's a reflective display. It will reflect the ambient light to produce the colors. So you need to put just a little power on the backlight unit. So the power consumption will be a lot lower than the current technology right now. So that will be a dream and the question, maybe the research topic to think about how we can apply this technology. And lastly, I would like to wrap up the feature prospect of this display technologies. I'm sure some of them you have seen in the market, but as I said, these are quite new and they are expensive. But if you go in a technology fair, the companies will showcase all these products, but there is a lot of research going on to make them available for all the products. So one technology is AR/VR technology. So some of the companies produces some augmented reality headsets, but there's still some room for improvement, and especially for manufacturing process. And micro LED will help actually to improve this technology, because micro LED is perfect for AR/VR technology. The other technology is transparent displays. So I don't know if you are interested in this, because this is transparent. So if you want to put this on your living room, you will be watching something on the screen, but you will be also watching your wall in the back. So this is like a usually advertisement thing, for the companies. So this is another research going on as this transparent displays. And we have holographic displays and flexible displays. So you can fold the display or roll them and have different, you have new applications in the field. So all of them are different questions and the topics that are now in going in the industry. So you might be interested in any of them. And as I mentioned in my previous slide, right now technology is evolving, but it's going very parallel with the research that you do. So whatever you do right now in your lab will be applied or will contribute to any type of display technology sooner or later. So that's all for me. Thank you very much. And if you have any question, I'll be happy to answer.
Can I ask a question? You mentioned about the definition of artificial intelligence. Do you have any project about it? Or just a plan?
We have a project right now. It's in the beginning stage. So we are using artificial intelligence actually for characterizing the displays, basically. So we will use it as a tool to design of the optical displays. Right now it's in the very beginning stage. So yeah, you're welcome. Any other question? Yeah.
Thank you very much for the talk, and sorry that
no problem.
But glad that I was here while you were talking about the e-ink displays. So we do know about the LCDs, we know about the backlight support through the LEDs, and also OLEDs, which does not need any backlight component. Compared to OLEDs, does the e-ink displays has any advantages?
Well, the first advantage would be the power consumption because it doesn't have a backlight. So it might be less than OLED. So I don't have exact numbers, but maybe power consumption might be less, as I assume. Because in the ambient light, it will reflect the ambient light to illuminate the screen. Might be the power consumption, first of all. And the other thing is the organic light emitter lifetime. So it eventually dies. Maybe this electronic ink will be better than that in that sense.
Very much.
You're welcome. No. Thank you very much.
Thank you, Dr. Serap, for this enlightening presentation. Before continue, we will give another break and we will meet again at 4 p.m. It's a great pleasure to introduce Dr. Alper Ülkü, distinguished professional in PhD candidate in Materials Science and Engineering at Gebze Technical University. Currently serving as a team leader, chief engineer of display technologies at Aselsan. Microelectronics, guidance, and electro-optics business sector, Turkey. Dr. Ülkü is an expert in thin film transistors, display materials, display optics, radiometry, and photometry. Today, he will share profound insights on advancements and future prospects in FinFET technology, providing a comprehensive overview of the transformative developments in FinFET technology. His talk covers historical backgrounds, motivations, and fundamental concepts, exploring critical aspects such as pin height, pin width, gate length, and role of the high K dielectrics in enhancing device performance. Please join me in extending a warm welcome to Dr. Alper Ülkü as he enhances our understanding of the future of the semiconductor devices.
Hello, I thank you for the introduction. I salute my professors, students, and my industry colleagues in the conference hall. I salute and thank to IYTE Department of Photonics and IZTECH-Photonics and Optics Society, IEEE Photonics Society for their hosting. I'm located in Ankara, Aselsan, right now. I'm grateful for invitation from Professor Canan Varlıklı. I also salute Professor Serdar Özçelik. How nice to meet again in a conference like this, and thank you for their kind invitations. And it's a distinguished opportunity to be here. Today I brief you today's and tomorrow's transistor technologies and opportunities to enhance performance of them. I'm a PhD candidate on material science and engineering under guidance of Professor Ahmet Yavuz Oral in Gebze Technical University, and I'm writing my PhD thesis regarding the thin film transistor materials and opportunities. Aselsan is the largest defense electronics company. We have been excelled in many fields of operation, and now we are designing airborne displays using both LCD and OLED technology. At my company, my profession is deeply in aviation electronics. My research team is a part of avionics systems design department, dedicated to developing cockpit displays compliant with aerospace and night vision compatibility standards. We have clean room processes for LCD and OLED display devices developed by our team of engineers of physics and material science. Today, I'll start with a brief intro to FinFET technology, then I'll try to summarize the gate dielectric materials used in transistors and FinFETs specifically. For some basic understanding, I'll try to go over dielectrics used in FinFETs. We will have a short introduction to functionally graded materials. And then I'll try to present the simulation tool and geometric model we are working on. Then the achieved results on this work I will present and state how to pursue this research that is related to my thesis work and leading to our product development. Let us start with the Moore's law diagram. That law states number of transistors on the microchip chips will double every 2 years, and this law still prevails. As the law has been not violated since 1970s, we constantly observe that the semiconductor companies are exploring ways to increase the transistor density per millimeter square in microchips. So nowadays, this density lies in the borders of 200 million transistors per millimeter square, where 1 millimeter square is the tip of my pen. Starting from 2013, chips have been fabricated employing this FinFET technology. So this is a $100 billion market that is dominated by Samsung, Intel, Taiwan Semiconductor Company, SK Hynix, and Micron Technologies. And within this market, in 4 nanometer technology nodes, I introduce you with the Ada Lovelace AD102 chip by NVIDIA that is produced by TSMC, just as an example of a FinFET microprocessor. This is the chip. It has been including 76 billion transistors in 600 millimeter square area, which makes the density 125 million transistors per millimeter square. So we are actually talking about 125 million transistors at the tip of a pencil. Well, as you've guessed, this means a lot in terms of application at all walks of life in biotech, nanotech, and artificial intelligence, which we should be calling it artificial superintelligence in the near future. So now you're looking at this mentioned FinFET that is used in these microchips. Fin field effect transistors are actually a type of non-planar transistors that came out of a need to overcome the limitations of traditional MOSFET designs. The name FinFET comes from the thin conductive channel that protrudes from the surface of the device that resembles the fish's fin, just like that. It protrudes to the gate. And this additional surface allows for a better control of the current flow, leading to improved device performance. It consists of the gate metal deposited on the gate dielectric, here the orange section, which is sandwiched between the highly doped N-channel silicon and the gate metal. Insulator we call here is a buried oxide insulator, box for short. Being a three-terminal device, FinFET source and drain connections are to be made on these thin walls via lithographic processes. The orange section is the gate dielectric that our workers will be concentrated on. We will try to enhance the performance of the FinFET via gate dielectric engineering with functionally graded materials using very well-known dielectric materials. So by FinFET, what do we achieve? By FinFET, we have maximum charge control with not one, not two, but three phases of gate metal. 1, 2, and 3. Thus, efficiency of the areas improved significantly. We have stronger depletion region that better inhibits the leakage current within the channel, and we have a superior channel performance since gate is almost all around the three phases. So these advantages have been employed over the last 10 years. But to our surprise, leading semiconductor company TSMC has already marked the end of FinFET era and announced they will start to commercialize the sub-nanometer scale, namely the 20 angstrom technology node. But before that, 2 nanometer node is planned to be implemented in 2025. Well, chip market is very competitive and disruptive market. We predict that the TSMC will still continue to fabricate FinFET microchips so that their market dominance prevails in coming years. So let me show you how this technology evolved in a very concise slide. Technology will continue its progress in another dimension nowadays. This is the third dimension. Becoming a third dimension just like here. First, we started with the planar FETs, maybe 80 years old, this technology, starting in the 1950s. And now we call the gate-all-around FETs will be employed. At least 3 times more transistors will be used in the same area. This is the FinFET, and this is the gate-all-around FET. So it utilizes all the area, but 3 times more transistor within the same area. And what now Samsung is doing is he had patented this so-called multi-bridge channel FET as source drain nanosheets reside on top of each other. So it's like a multi-story bridge separated by same gate metal and the dielectric structure. More here, a better view of this gate all around structure is here. You see all gates all around the channel and dielectric within, sandwiched between source gate channel and the gate. So, but how did this all begin? In the beginning of our century, 21st century, only 20 years ago, we gradually observed 6 stages of thin film transistor development. And here we expose some figures from our review paper. These phases of development starts with the bulk planar architecture. This is the single gate bulk planar architecture. This is very similar to MOSFET, but you see, it's not the PNP junction, it is junctionless transistor. We don't have a junction here. It's an N-channel, highly doped N-channel structure. So this is we call the bulk planar JL-TFT, junctionless TFT. And then the box is introduced since it confines the channel and have a better channel performance. And then high K dielectrics on the walls of the gate oxide and gate has been introduced in the 2005-6s. And then more gates metals are used with the gate 1 and gate 2 being different metals and different work functions of metals. A single oxide and box together used in another alternative architecture. And all of a sudden, the cell box came, the selective box. What did this had advantage? This is the advantage of the cell box leading to the FinFET. This is the protruded structure of the FinFET, you know, here. And this is the cell box. Look how it resembles themselves. We leave the bulk and put a cell box here, which is the dielectric here, and dielectric in that dioxide. That these can be different dielectrics or the same dielectrics, starting from the silicon dioxide and other materials, of course. And then it all evolved to FinFET in 2010s and started to commercialize at 2013s. It's a better 3D representation is presented as in this architecture evolution. This is the planar, this is the gate dielectric with the FinFET, and this is the bulk FinFET, and it's a soy FinFET. That's a buried oxide. And another representation is here. We capture 3 types of FinFETs in one slide here. The difference between them is the first one is the shorted gate FinFET, where the dielectric thickness of the gate is single and constant. We don't change the dielectric thickness of the gate in the gate 1, gate 2, gate 3. In the second one, independent gate FET uses only 2 gates. There is no top gate here and the dielectric, only 2 gates and 2 dielectrics sandwiched. Sandwich is the source drain channel. And at the end, the tri-gate FinFET, it is the rock star. It is the technology used today in the fabs. And dielectric thickness of the third gate is slightly higher than the other thicknesses. Gate 1, gate 3, and gate 2. Gate 3 dielectric thickness is slightly higher than the other gate dielectric thicknesses. And this is what is happening in the fabs. So why? Because instead of 90-degree fin structure, more than 75-degree inclined fins are used to ease the deposition of dielectric material evenly on the silicon channel. So this is much more easier to fabricate instead of these ones, as any nanotechnology person can imagine. So now you're looking at the masterpieces of newest technology. These are the state-of-the-art fabrications and called GAA FETs, the gate-all-around FETs. These are multi-story buildings, like multi-story transistors. You can observe that the drain and source metals evolved as a wall of conductors, the red side, and cyan-colored spacers are the dielectrics. And when you look at the BB cross-section here, you can see the source drain channel as an oval structure here. These are channels. So these are common gate transistors. These are common gate 3 transistors. Okay, so if you want to have for example, common gate in a CMOS gate or another gate you are implementing, you can use this structure. But of course, there are many parasitic effects and capacitance effects affecting these 3 transistors, and cross links and cross currents and drain currents are crossing themselves. You have to solve these problems in order to continue with this design. And this is another Samsung patent, and they are now trying to produce right now. It's another masterpiece and future prospect or the FinFET technology. It is called the multi-nanosheet FET. We have 2 types of them. One with the box, BOX here, and the other one is without the box here, without the box. So a bottom oxide, you know, bottom gate oxide, not the gate oxide, the bottom oxide. So these have been now worked and patented, and we have 4 instead of 3-story channels built by a very, very complex 3 nanometer lithography process. It would be a logical thinking that if all parasitic capacitances and crosstalk current problems are all mitigated, we will, the world will be starting to observe a height changing the microchips so that their height might increase in coming decades. It's a 3-story building. That building might be having some more stories. So on top of these, we have conducted a performance-wise review and on the latest literature, comprised of more than 70 papers within the last 3 years. And we observed that the FinFETs with dual and triple heterogate structures, which means multiple dielectrics, and trigate FinFETs achieve the best performance. And the trigate being the rock star holding the stage right now. Our performance metrics were the subthreshold slope, drain-induced barrier lowering, and ion-IF ratio, which are the primary metrics to evaluate thin film per transistor performance. So let me tell you about these performance parameters, and let us consume some time on these next 2 slides, as these are the most important figures of merit for evaluation of FETs. Every transistor has a threshold voltage VT, where transistor switches its regime to pass a significantly high drain current. When we change the structure of the transistor by design, say when we add a different dielectric or change the channel width or change the channel length, this threshold voltage naturally changes. So when the VDD supply voltage ranges from some millivolts to some volts, the VTH, the threshold voltage also changes slightly. We call this change the drain-induced barrier lowering. This is an unwanted effect. So it should be a typical metric to minimize. It is needed to measure how efficient our effort is to control the channel current. It is defined as the difference between these 2 voltages when our drain supply is between 2 extremes. So when we change the VDD from 0 volts to 0.8 volts, for example, how much this VTH changes is the drain-induced barrier lowering performance parameter. It has 2 adverse effects. One is the off current increases with the changing VTH. And second, you may need to reprogram the operation of the transistor for different drain voltages. Thus, the operation becomes a very complex one, and you don't want to do this. So Dibble is a very important parameter in evaluation of FinFETs and other FET architectures. So one parameter was DIBL. The second parameter is the subthreshold slope. It is almost the reciprocal, it is almost the reciprocal of the transconductance of the transistor. But here we can take the natural logarithm of drain current so that the unit of subthreshold slope becomes millivolts per decade. When you are using silicon as channel, subthreshold slope is usually at the magnitude of 60 millivolt per decade. This is the slope, and it's about the transistor's speed. If subthreshold slope is steep, your transistor will be a high speed transistor. So it's a very important parameter, of course, in transistor design. So that's why they're now passing to indium gallium zinc oxide instead of silicon. This is the reason they are passing to and using azo, exo materials since the subthreshold slope of these materials are much higher and better than silicon. And our third parameter is the ion-IF ratio. As the name implies, and the current with the VGS greater than the threshold. Ion is the largest current with the VGS greater than the threshold. IF is the maximum current passing from drain to source. Even we shut the transistor down with VGS the way below the threshold voltage. So that is the ratio between them. Ion-IF ratio is the ratio between our on current, maximum on current, and minimum off current. So this is another performance issue that we have to take into account in transistor design. And what about the dielectrics? So companies have been utilizing many types of gate dielectrics. You may be seeing them in the slide with their kappa, namely their dielectric constants, will vary from 3.9 to 80. And their band gaps vary from 3.5 electron volts to 9 electron volts. In order to isolate the gate metal and form a proper electric field, to control the drain current, gate dielectrics are of great importance. But what do you notice here? Look at this table, and what do you notice here? Let's see. The problem in this table is we have no oxide dielectric between kappa greater than 30 and less than 80. There's a huge gap between these numbers. There's no 40, 50, 60, or 70 kappa dielectric. So the highest kappa is, if it's an oxide, it's a titanium dioxide. And the least one is the, hafnium dioxide and lanthanum trioxide. And it has a kappa of 30. So band gaps around 6. So now our proposition becomes such that what if we generated materials between these properties that behaves better than hafnium dioxide? FGMs, the functionally graded materials, may provide us some space to engineer new gate oxide between these values and at least try to these gate dielectric materials with different dielectric constants. So let us have an introduction here on functionally graded materials. These are actually a derivative of composite materials where a certain material property within its property is not evenly distributed. Rather, it changes with the thickness at x-axis, y-axis, or z-axis. By looking at the pictures, you might easily sense how this grading is achieved. Grading is either continuous or stepwise, and it can be either a material composition, orientation of molecules, or fractional gradient. In case we have a continuous profile, grading can be linear, like that, linear, or it can be an exponential law, or it can be a power law. So linear profile, the material property will change with the linearly from one surface to other. So exponential power or nth power of thickness can be used also for grading. And most common, the sigmoidal profile from one end to the other is used in generating functionally graded materials, which is a hyperbolic tangent function. We may also have different phases of material neighboring each other, so that as thickness is varied, the material property changes from phase A to phase B, which means that this is a single FGM. We have two materials, and as one material concentration increases, the other material concentration decreases, shown here. In a double FGM, you have three separate materials, so that while thickness changes, the material properties varied as seen in this figure. Starts with A and continues with C and ends up with B material or property. So in this work, we'll try to have some simulations with double FGM materials used as gate dielectrics. For example, first of all, we need to have a natural example or examples from nature, let's say. We see here, for example, a metal to ceramic FGM, which apparently the porosity of the porosity property changes from one side to the other in the north side of the material. For starting when we go to north of the material here, okay, there are some the material property of porosity changes. So it all starts with the metallic phase and ends up with the ceramic phase. So you see material gradually changes to a ceramic. So there are other examples from the nature that bark of a tree, human nail, human teeth are some natural FGM materials, so that material property, for example, density, porosity, or dielectric constant changes with the z-axis of our depth of the material. And if it is an epsilon FGM, what happens? So when we introduce the Greek letter epsilon, it means that the material property is changing with a certain rule or formula. Either this is independent variable, this may be thickness or its powder density, dielectric constant. And in this example, an epsilon FGM is the effective permittivity of the material will vary according to a two-dimensional parameter, power the weight density, and it's formalized with the Maxwell-Garnett equation showing here. After this introductory knowledge, now our research question became, can we enhance gate dielectric performance via these epsilon FGMs? So before start, let me introduce you Silvaco tools. It's a part of our methodology using Athena and Atlas for this purpose. Without trying these FGMs in the laboratory first, we need to simulate them, which might be practical for and saving you time before manufacturing. So Athena is the definition for definition of material structure and process engineering. Even you can simulate your processes here, and then you can introduce electrical excitation with Atlas. So your defined structure can be characterized in simulation with Atlas tool. Of course, there are many Silvaco tools, but these are beyond scope of our work today. So what happens in our tool? Our simulations are now on a FinFET that are defined as follows. Normally, single dielectric lies sandwiched between the silicon channel and the top gate, magenta. And our parameters for this FinFET are as follows. Our gate work function will be 5 electron volts. It is near to copper, nickel, or gold. Doping concentration is 5 times 10 to the power 19 per unit centimeter cube. Fin height is 5 nanometers, fin width is 2 nanometers, channel length is 14 nanometers here to here, and our wire length is here to here 34 nanometers. Here first we will employ the single layer dielectric between gate and source drain channel, and then we'll try to modify this with a 3-step FGM, or in other words, a double FGM. So what happens now with a single dielectric? Let's have our control group, okay? We need a control group. We have to first simulate all we have, the single layer dielectrics with our FinFET, okay? So we start with a single dielectric as a single layer. In the left-hand side, we observe that the changing gate dielectric also changes the threshold voltage of the FinFET significantly. And the threshold voltage will start from 0.5 volt here. It is the silicon dioxide added as the dielectric here. And at the other end, the titanium dioxide added as a dielectric will be having a much higher threshold voltage, around 1 volt. And on the right-hand side, not only the threshold voltage changes, but the logarithmic version of the same graphic is read as, it is apparent here that not only the threshold voltage, but the off current changes significantly. The off current of the titanium dioxide is very, very low. And the off current is silicon dioxide, and the dielectric is much higher. The difference between them are at the maybe 8 orders of magnitude. It's really significant. So off current can be reduced by increasing the dielectric constant, but carefully, of course. But we have to care all the interface properties of materials before doing that. And I'd like to summarize all the single dielectric kappa of FinFETs in a single slide. Okay, what about this slide? We have DIBL, the drain-induced barrier lowering in the first graphic. It is decreasing with the equivalent kappa. Okay, when you increase the kappa, you're now decreasing the drain-induced barrier lowering, which is a good thing, until hafnium dioxide. Until hafnium dioxide, it is very efficient. But when you further increase the kappa, it does not increase, it increases. Lanthanum trioxide doesn't do us any good, and titanium dioxide even doesn't have any advantage with respect to the hafnium dioxide. So that may be a big advantage of hafnium dioxide also when looked from the electrical perspective, okay? And the ion-IF ratio also has a local maxima at hafnium dioxide. The ion will be having, it will be on maximum at silicon dioxide dielectric, and will be minimum at titanium dioxide. And for example, the VTH, the threshold voltage, will be increased at silicon dioxide, alumina, hafnium dioxide, lanthanum trioxide, and titanium dioxide. It's like a curve of exponential. So this is, I mean, this cannot be eliminated since you increase the dielectric constant, but it will take a different shape when we will be using the FGMs. So the subthreshold slope, it is inevitable to have a 60 millivolt, but this cannot be further decreased lower than 50 millivolts. It remains constant at 56 millivolts as shown here. So there are 3 systematic deficiencies here. With a single dielectric material, DIBL, the drain-induced barrier lowering, does not decrease after kappa greater than 22. So max drain current does not increase until kappa equals 80, and the V threshold increases constantly with increasing K, which may not be preferred. I mean, increasing dielectric constant more will not do us any good because it increases the power of the transistor. So that may not be good. But what happens when we have the FGM, we'll see in the next slides. And additionally, I should be stressing on the using the titanium dioxide neighborhood, this is, as stated in some papers, it is a problematic neighborhood. So non-matching gate oxide kappa leads to divergence of off currents. If you directly put the titanium dioxide on top of silicon, it may be causing divergence of off currents. It's not a problem in on current, but we have a divergence of off currents, which may be a problem. It's an order of magnitude different. So this is the sign of the abnormality of the silicon to titanium dioxide neighborhood. So how can we overcome these limitations? So we started by engineering 12 FGMs. These are the single dielectric cases, all 3 nanometers. I showed you in the previous slides. All 3 nanometer single dielectrics at my top table. And these are the first set of experiments. And the second set of experiments will incorporate the generated FGMs using stepwise manner shown here. For example, an FGM of C will have an equivalent kappa of 20 when we add 0.5 nanometers aluminum, 2.5 nanometers of hafnium dioxide, sorry, alumina, and all will add up to 3 nanometers. Okay, I mean, we should not be changing this to make our experiment fair. For example, the G dielectric, let's see the G FGM, it will have all ones here: alumina 1 nanometer, hafnium dioxide 1 nanometer, and titanium dioxide 1 nanometer, all adding up to 3 nanometers. So this will have an equivalent kappa of 38. Now we are exploring the regions, unmapped regions of dielectrics in the region of dielectric constants, ranging from 30 to 80. So equivalent kappa is, of course, calculated with the thickness weighted average of individual kappas building the individual FGM. So grading profile will be just like this. For example, for E, silicon dioxide, alumina, and titanium dioxide. And for FGM-F, silicon dioxide, hafnium dioxide, and titanium dioxide on top of each other. So our results for the 12 FGM for the DIBL would be as follows. The first is the drain-induced barrier lowering parameter. We observed that the D and G FGM has slightly lower drain-induced barrier lowering parameter and having a better result when looked at from other points of view also. So D, we have 0.5 nanometer of alumina, 2 nanometer of hafnium dioxide, and 0.5 nanometer of titanium dioxide. And the G is all ones here, adding up to 3 nanometers. So very interesting. So when you add these on top of each other, you apparently change their interface properties. So that our interfaces become much smoother here, much smoother. So for ion, for example, the ion becomes a better one when we have, you see the orange curve here. D, G, F, and H have significantly higher on currents, so better than hafnium dioxide and titanium trioxide. But of course, we will be having a silicon dioxide has the biggest ion, but we don't have to use the silicon dioxide for our new designs since it has lesser capabilities as a single dielectric. So maybe these can be used also in a new design when the F, G, and H are having such properties. Just we change the thicknesses of the dielectric material. And for the off current, we have some opportunity here, both here and D and G, as I said, they both have a lower DIBL and lower IOF, better than lanthanum trioxide. It is very near to hafnium dioxide's off current. But K, L, and M has much better off current values here without reaching the titanium dioxide. For example, M has a slight of 0.5 nanometers of hafnium dioxide and 2.5 nanometers of titanium dioxide. So the VTH, the threshold voltage, which we should be minimizing, we have also opportunities here. We have advantages for A, E, F, and H, and J with equivalent kappas of 12, 32, 35, 42, and 43. These are much better appearing from hafnium dioxide. And lastly, ion-IF ratio. Of course, ion-IF ratio locally, hafnium dioxide is the king here, but when you increase it, it won't be increasing until G, but it will be increasing more. K, L, and M will be having better ion-IF ratios than hafnium dioxide. So we have an opportunity here also. And SS won't be changing any good. I mean, it won't be making many big progress, but it's because of the silicon. This is when you use silicon channel, you won't be making any differences in interfaces and SS. When the x-axis becomes equivalent band gap, V threshold becomes like that. You have now some opportunities here. The V threshold becomes less when you want to do this with some composite dielectrics. The F, J, H, B, E, and A are now have better threshold voltages than the hafnium dioxide. So we have created unmapped dielectrics with the FGMs. And so which dielectric we should be choosing then? I mean, we have some opportunities, okay, fine. Functional grading allows seamless transition between different material properties, reducing the likelihood of failures due to abrupt changes in material characteristics. Thus, interface problems might not be there anymore, might be mitigated by FGMs, but we should be using that. So I introduced another figure of merit for evaluating a transistor with the FGM and also without an FGM. We asked ourselves, well, how shall we evaluate this architecture numerically? So that the desired variable we need is to be maximized, should be on the numerator. So desired variable we have to minimize should be on the denominator. So that we have a new form. Let's call it the FET form or FGM form, figure of merit. So we define a performance parameter just like that. So what happens when we define a parameter? The VTH to the power 5 and DIBL to the power 2 means that I penalize the VTH more than any other parameter. This is the most important parameter for me, for example. So I penalize it by 5. And I penalize the double by 2. So, I mean, it's a squared of double and fifth power of VTH. So this means that we care for these parameters most. Okay. And as a result, what we have, the FGM or FET form, we evaluated the single material dielectrics here with this form, and hafnium dioxide takes value very similar to titanium dioxide. But if you have a titanium dioxide, you'll be having a problem. We won't have been trying that. So when it's alone. So hafnium dioxide is quite good with respect to other single material dielectrics. That's obvious here. But when you introduce the FGMs, you see that D, G, and M are slightly higher than hafnium dioxide's figure of merit. So when we have a foam like that, it is evaluated that G material, which is, for example, alumina, hafnium dioxide, and titanium dioxide used together, will be forming a G dielectric. And having an equal kappa of 38 will be better behaving as a gate dielectric. Okay, so that is how we evaluated our simulation. So this is the achieved FGM. First, we deposit alumina on top of silicon, and then hafnium dioxide, and then titanium dioxide, so that our grading is achieved in a stepwise manner. Of course, we have to be simulating the sigmoid function maybe, but in the very near future. So as a result, equivalent dielectric constants around 35 and 45 kappa gave better results than hafnium dioxide. So I want to thank you all for listening to me, and if let us leave some space for your questions. And I'd like to thank you, first of all, Professor Canan Varlıklı and her İYTE research team that enabled this event to happen. I'd like to acknowledge my professors and my colleagues in my team. So I'd like to thank them all. So it was a real hassle without them. So this is the display research team at Aselsan. I thank you for your listening, and my primary aim was in this presentation is it is importance of the subfield of technology is important that we are trying to attain a product, airborne product, so that we will use the OLED technology with this TFT, not buying a TFT anymore, but making our own TFT back panel. Thank you for listening. I may entertain some questions, of course. Thank you very much.
Thank you very much, Alper Hocam. It's been a great talk. And thank you very much for accepting whenever we ask you to give a talk, you never reject us. Thanks a lot for that.
Thank you.
So anyone who would like to shoot a question? I know there are people who are interested in transistors. Yes, one of them has raised.
Thank you for your inspirational talk. I just wondered the FGM, you got some aluminum oxide, titanium dioxide like this. Is your layer structure important? For example, you need to put titanium first and the aluminum, or you try to mix them and you got different results. I just wonder that.
Well, of course, this is an interim result. We have to now produce it. I mean, at Aselsan, we are now in the, of course, not nanometer, but micrometer technology. We have some 100 nanometers, but our lithography process is now around microns, of course. But we have to know the problems of the near future and future, so that our technology will advance in that current sense. So we are at the verge of now having these simulations and productions together with our OLED technology inside. on site. So we are, of course, having our universities helping us on this endeavor. So in the next maybe 6 months, we'll be having some prototype of TFTs and maybe FinFETs. So we will be trying these transistors together with our OLED technology. So we'll be happy when we have a nice result. We'll be happy to share again.
Thanks again.
Thank you.
Is there any other question? I think not. So thank you again, Dr. Ülkü, for your inspirational talk. Also,
thank you very much.
As the fourth-year photonics students and former president of IEEE Photonics Society and one of the founder members of IZTECH-OPS and Photonics Society, I would like to thank, and on behalf of İZPHOTECH 23 team, all our participants and who were with us during the two-day period, all of our speakers who attend both face-to-face and online, and finally, all of our members who made this possible. I hope we have been able to appreciate the presence of photonics in our lives. Please don't forget to fill our evaluation form. I hope to see you all next year at İZPHOTECH 24, but till then, may the light be with you.
Evaluation form vardı. Gençler onu yansıtacaktınız.
Seni buradayken çıkarmak.